On July 1st, 2025, the Atlas telescope in Chile picked up something moving through space, fast, 36 miles per second, mass estimated at 33 million tons, roughly the size of Manhattan. The trajectory calculations came back with a result that made every astronomer sit up straight. External origin. This thing came from beyond our solar system, the third confirmed interstellar visitor in the entire history of human observation. They gave it the designation 3I/Atlas. Observatories around the world swung their instruments toward it. Then Harvard Professor Avi Loeb stepped forward with a statement that fractured the scientific community right down the middle. He claimed to have identified 6 distinct signs suggesting this object might be artificial, a spacecraft. Then the data got weirder. Fresh analysis revealed the object is emitting a nickel alloy, the kind aerospace engineers use to build rockets and satellites, something nature has never been documented to produce on its own. Over the next 2 hours, you're going to learn everything we know about this visitor. We'll dissect each of Loeb's 6 pieces of evidence. We'll hear what the skeptics are saying. You'll find out what the Mars Express satellite actually captured on October 3rd, when this object made a dangerously close pass by the red planet. And right at the end, I'm going to show you data NASA published just 1 month ago. They found a rock on Mars that could represent the most compelling evidence of extraterrestrial life ever discovered. Stay with me until the very end, because that's when I'll tell you about a planet 120 light-years away, where the James Webb Space Telescope detected a specific molecule. On Earth, that molecule means only one thing: life in the ocean. Here's something most people don't realize. We've only been detecting interstellar objects for 8 years. Before 2017, we had 0 confirmed visitors from other star systems. The reason was straightforward. We lacked the technology. Vladimir Surdin, an astronomer at Moscow State University, puts it simply. February 15th, 2013. A meteorite detonated over Chelyabinsk, Russia. The shockwave shattered windows in thousands of buildings across the city. More than 1,000 people sustained injuries. The world woke up to a terrifying reality. We're vulnerable. That asteroid measured just 56 feet across, and look at the damage it caused. Imagine something larger. Suddenly, money started flowing into detection programs. Countries began constructing networks of robotic telescopes, automated systems designed to spot dangerous objects before they get too close. Moscow State University built their own array. The Americans erected more powerful installations in Hawaii and Chile. By 2015, astronomers had become what Surdin calls eagle-eyed. Today we catch almost everything crossing our celestial neighborhood. October 19th, 2017. The Pan-STARRS telescope in Hawaii flagged an unusual object. Scientists calculated its trajectory, and the answer was unambiguous. Not from here, the first interstellar visitor we'd ever observed. They named it Oumuamua, which translates from Hawaiian as first messenger from afar. The shape stopped everyone cold, an elongated cigar, possibly 1,300 feet long. The length-to-width ratio hit roughly 10:1. Among the 5 million asteroids catalogued in our solar system, nothing even comes close to that profile. Absolutely nothing. Oumuamua had no tail, no signs of evaporation. It moved through space like a solid chunk of rock. Astronomers started building predictive models for its trajectory. That's when they hit the anomaly. As Oumuamua moved away from the sun, it decelerated more slowly than gravitational physics predicted. Something appeared to be giving it a push. Extra acceleration from an unknown source. Enter Avi Loeb, full name Abraham Loeb, born in Israel. Harvard graduate who now chairs the astrophysics department at that same institution. Published researcher with hundreds of citations in major journals. Surdin makes a point of emphasizing this. Loeb knows his field inside and out. He's a legitimate professional astrophysicist, not some internet conspiracy theorist cooking up wild theories for clicks. Loeb proposed something radical. What if that anomalous acceleration came from a light sail? That's technology we're actively developing right now for potential interstellar missions. Could Oumuamua be a probe dispatched by an alien civilization? Maybe wreckage from one of their spacecraft? The scientific community erupted. Some researchers called the hypothesis courageous and worthy of serious investigation. Others accused Loeb of publicity-seeking behavior. The object zipped past too quickly. We gathered insufficient data before it vanished. Oumuamua disappeared back into interstellar space, leaving behind far more questions than answers. A recent study from 2025 offered an alternative explanation. A team of scientists suggested Oumuamua might actually be a fragment of what they're calling an exo-Pluto. Picture an icy exoplanet from a completely different star system that somehow broke apart. A brand new category of cosmic object. The thing is, this hypothesis still doesn't account for all the peculiarities we observed. The debate rolls on. August 2019, Gennady Borisov, a Russian astronomer working at Moscow State University and the Astronomical Institute, spotted the second interstellar object. They called it Comet Borisov, designation 2I, with the I standing for interstellar. This one displayed all the classic comet characteristics: visible tail, developing coma, active evaporation. It just happened to originate from another star system. Scientists analyzed its spectrum, studied its chemical makeup, tracked its behavior. Nothing unusual stood out. Comet Borisov failed to generate the same level of excitement as Oumuamua. Astronomers actually felt relieved. Here was proof that normal interstellar comets exist. Not every visitor from beyond has to be bizarre like the first one. Then number 3 arrived, July 1st, 2025. The Atlas system registered a new object carrying the temporary designation A11PL3Z. Initially, they posted it to the Near-Earth Object Confirmation page. More observations refined the orbital calculations. The conclusion became clear: another external origin case. Additional data revealed the object had actually appeared in archival images dating back to June 14th. The reason nobody spotted it earlier makes sense. It was crossing through the dense star fields surrounding the galactic center. Try picking out one moving object against thousands of background stars. By July 2nd, multiple observatories in Chile, Arizona, and Hawaii had all confirmed the same thing. The object possesses both a coma and what appears to be a developing tail. The Minor Planet Center made it official. Designation 3I/Atlas, third interstellar object. Another comet. Avi Loeb wasn't buying it. He immediately started gathering every scrap of data available: trajectory analysis, spectral measurements, thermal signatures. Then he went public again with another announcement. 6 specific characteristics that concern him deeply. 6 potential indicators of artificial origin. Let's go through them one by one. First characteristic: entry trajectory. This object entered our solar system almost perfectly aligned with the ecliptic plane. That's the flat disk where all our planets orbit. Mercury, Venus, Earth, Mars, Jupiter, Saturn. They all circle the Sun in roughly the same geometric plane with only minor deviations. Interstellar objects can approach from literally any angle, 360 degrees of possibility. The statistical probability of threading the needle and entering right along the planetary plane is exceptionally low. Cerdin acknowledges the odds are slim, but rare events do occur. When you're dealing with a single event, calculating meaningful probability becomes problematic. Loeb counters with this: if this object is a spacecraft, that trajectory could represent a deliberate choice. Why? To fly past the interesting targets, the planets. Second characteristic: close approach to Mars. October 3rd, 2025. 3I/Atlas passed dangerously close to the red planet. The Mars Express satellite, a joint European-Russian mission, managed to photograph it during the flyby. Teams are processing that data right now. Multiple robots operating both on the Martian surface and in orbit had front-row seats. A genuine opportunity to examine this object at close range. Loeb poses the question: coincidence? Or did the object deliberately use Mars's gravitational field for a course correction? When a spacecraft flies past a planet, it can exploit that planet's gravity to alter its trajectory. NASA calls this a gravity assist maneuver. We use this technique routinely. The Voyager probes flew past Jupiter and Saturn, using their massive gravitational fields for velocity boosts. What if 3I/Atlas is executing the same kind of maneuver? Third characteristic: gas envelope with zero trajectory deviation. The object is wrapped in a visible coma. A tail is developing behind it. From a distance, it looks exactly like a comet. But actual comets behave very differently. When a comet approaches the Sun, solar radiation heats the ice on its surface. That ice vaporizes. Jets of gas explode outward. Those gas jets function like tiny rocket engines. They push the comet around, causing deviations from the predicted orbit. Every sun-heated comet starts what Cerdin calls wobbling. The trajectory shifts slightly, unpredictably. Here's what makes 3I/Atlas strange. Visually, it resembles a comet. Behaviorally, it flies like a solid rock. Perfect adherence to the calculated gravitational trajectory, zero wobble. Loeb describes this as camouflage. The object is disguising itself as a comet while actually behaving like a controlled craft with thrusters compensating for any unwanted deviations. Fourth characteristic: size and mass. Early estimates suggested a diameter reaching 12 miles. Mass calculations came in around 33 million tons, absolutely enormous, comparable to Manhattan in physical scale. Later observations from the Hubble Space Telescope revised those numbers downward. New estimates suggest a diameter somewhere between 1,000 feet and 3.5 miles, probably under a mile. Even with that correction, it's still substantially larger than Oumuamua, which raises an interesting question. Why didn't an object this large get ripped apart by tidal forces during millions of years of interstellar travel? Space between the stars is violent. Objects collide with debris. Stars exert gravitational stress during close passes. Maintaining structural integrity across that kind of distance and time span represents a significant engineering challenge, whether natural or artificial. Fifth characteristic: chemical composition. The James Webb Space Telescope ran a spectral analysis. Results show the object contains unusually high concentrations of carbon dioxide. Also present are water ice, water vapor, carbon monoxide, and carbonyl sulfide. The Very Large Telescope in Chile detected emissions of cyanide. Then came the detail everyone's arguing about, atomic nickel. Some scientists say the concentrations match what we see in regular solar system comets, but data published on October 18, 2025, revealed something nobody expected. The object appears to be releasing a specific nickel alloy, the kind aerospace engineers select for building rockets and satellites. This particular alloy has never been identified in any natural cosmic object, ever. Loeb jumped on this finding immediately. Natural geological processes don't manufacture aerospace-grade alloys. Only advanced technology does that. Sixth characteristic, potential for additional maneuvers. The object hasn't left yet. On October 30th, it will reach perihelion. That's the closest point to the Sun in its trajectory, distance of roughly 1.4 astronomical units. After that, it makes a relatively distant pass by Venus. Earth gets an inconvenient viewing angle. The Sun will be positioned directly between us and the object during its closest approach to our planet. By the end of December 2025, current models predict it will exit the solar system entirely. Loeb suggests we shouldn't assume that's guaranteed. If this is a spacecraft, it could perform another gravity assist, use Jupiter's enormous mass, or Saturn's, to radically alter course, maybe even redirect toward Earth. The next few months will tell us everything. If the object suddenly changes trajectory in a way that gravitational physics can't explain, we're looking at the biggest story in human history. The scientific establishment responded exactly as you'd expect. Most professional astronomers shake their heads when the alien spacecraft hypothesis comes up. Some smile politely. But here's the thing. They still respect Loeb. Surdin emphasizes this point repeatedly. Colleagues might disagree with his conclusions. They might think he's gone too far out on a limb, but they acknowledge his expertise. He's a real scientist who understands the subject matter deeply. Sky at Night magazine published an article with a pretty definitive headline. No, our solar system's interstellar visitor is not aliens. Here's the science to prove it. They argue the expanding body of observational evidence points clearly toward natural origin. Wired magazine described how 3I/Atlas is essentially spraying water like a cosmic fire hydrant. The Neil Gehrels Swift Observatory data suggests this interstellar comet probably has internal structure quite different from comets native to our solar system. Different, but still natural. Still a comet. Surdin offers a philosophical take on the whole situation. If Loeb ends up being right, he becomes the hero, the scientist who saw what everyone else missed. If he's wrong, people forget and move on to the next controversy. So why not take the long-shot bet? In gambling terms, Loeb went all in. He staked his entire scientific reputation on this hypothesis about artificial interstellar visitors. For an established researcher at his level, that's either incredibly brave or incredibly reckless. But look at the history of science. How many ideas seemed absolutely crazy at first? Continental drift, the theory that bacteria cause stomach ulcers, dark energy. Every single one of those concepts got ridiculed initially. Later, they handed out Nobel Prizes. Loeb keeps digging for more evidence. After Oumuamua, he launched a project to search historical archives for other potential interstellar visitors we might have missed. His team combed through records of meteorites entering Earth's atmosphere over the past several decades. One particular meteorite caught their attention. It slammed into our atmosphere at extraordinary velocity. Objects orbiting within our solar system don't achieve those speeds. The sun's gravity prevents it, which means this thing came from somewhere else. Loeb traced the trajectory backwards. The meteorite disintegrated over the Indian Ocean, so Loeb chartered a yacht, assembled a crew, and went looking. They deployed magnets on the ocean floor at depths around 10,000 feet, recovered tiny metallic spheres from the seabed, sent those samples to a laboratory for detailed analysis. The results shocked him. The alloy composition doesn't match any known terrestrial material. Nobody on Earth manufactures alloys with that specific signature, according to Loeb. He's calling these spheres debris from an alien spacecraft. Skeptics push back hard. Could be contamination, industrial waste from sunken ships, terrestrial debris that settled on the ocean floor over decades. The argument continues with no resolution in sight. August 30th, 2019, Gennady Borisov operates his own telescope at the Margot Observatory in Crimea. He built the instrument himself, 65 centimeters in diameter, modest by professional standards. But Borisov knows the sky intimately. He observes methodically night after night, scanning the same regions repeatedly. That evening in the constellation Cassiopeia, he spots a faint fuzzy patch moving against the background stars. Something unfamiliar. He checks every database available. Nothing matches. Borisov submits his observations to the Minor Planet Center. Other observatories confirm the object within days. They calculate the trajectory quickly. Orbital eccentricity exceeds 3, a hyperbolic path. The object arrived from interstellar space and will return there. The second interstellar visitor receives its designation, 2I/Borisov. Borisov becomes the first person ever to discover an interstellar object using amateur equipment. Comet Borisov behaves exactly as expected. Classic cometary tail develops. Active coma surrounds the nucleus. Spectroscopic analysis reveals water, carbon monoxide, cyanide. Everything astronomers predict for comets. Teams around the world track it eagerly. The Hubble Space Telescope captures detailed images. Ground observatories in Chile, Hawaii, and Spain collect data continuously. Scientists compare its composition to comets born in our solar system. The match is remarkably close. Borisov contains similar ratios of volatile compounds, similar dust-to-gas ratios, similar activity patterns as it approaches the Sun. Professional astronomers actually feel relieved. Here's confirmation that normal interstellar comets exist. Oumuamua might have been the oddball, the exception rather than the rule. Borisov validates their understanding of how comets form and evolve across different star systems. By January 2020, as Borisov races back toward interstellar space, the scientific community reaches a comfortable consensus. Interstellar objects will occasionally wander through our neighborhood. Most will resemble the objects we already know. Asteroids will look like asteroids. Comets will look like comets. The universe operates according to consistent physical laws everywhere. Fast forward to July 1st, 2025. The Atlas telescope in Rio Hurtado, Chile, is running its automated survey program. ATLAS stands for Asteroid Terrestrial Impact Last Alert System. NASA funds this network specifically to detect potentially hazardous objects. 4 telescopes operating across Hawaii, Chile, and South Africa scan the entire visible sky every 48 hours. The Chilean station flags an object moving through the constellation Sagittarius. Apparent magnitude 18, extremely faint, visible only through powerful telescopes. The automated system assigns a temporary designation, A11PL3Z. Software calculates a preliminary orbit. The numbers look unusual. High velocity, steep trajectory angle. The Minor Planet Center receives the report within minutes. They post the object to the Near-Earth Object Confirmation page. That posting triggers an automatic alert to hundreds of observatories worldwide. Professional and amateur astronomers immediately start hunting for this object in their own images. Within hours, the Zwicky Transient Facility in California finds the object in their archive. Images from June 28th and 29th clearly show it. They dig deeper into older data. More detections appear. June 21st. June 14th. The object has been visible for weeks. Nobody noticed because it was crossing directly in front of the galactic center. Picture trying to spot one dim, moving dot against the backdrop of millions of bright stars clustered together. Nearly impossible. Amateur astronomer Sam Dean combs through Atlas archives from other stations. He finds even earlier observations. June 5th. The object entered detection range almost a month before anyone flagged it. Scientists later estimate it crossed Neptune's orbit sometime in late 2024. It's been traveling through our solar system for almost a year, completely undetected. July 2nd brings critical observations. The Deep Random Survey Telescope in Chile captures images showing something unexpected. A faint, fuzzy envelope surrounds the point of light. The Lowell Discovery Telescope in Arizona confirms it independently. The Canada-France-Hawaii Telescope on Mauna Kea sees it too. A coma, roughly 3 arcseconds across, with a subtle tail-like elongation pointing away from the Sun. This object isn't an asteroid. It's actively outgassing. A comet. The Minor Planet Center makes the official announcement that same day. They assign the interstellar designation, 3I, third confirmed interstellar object. They also give it a cometary designation, C/2025N1, using the Atlas survey name. By the time the announcement goes out, the center has collected 122 separate observations from 31 different observatories around the globe. The astronomical community mobilizes instantly. Major observatories begin scheduling dedicated observation time. The James Webb Space Telescope adds 3I/Atlas to its target list. The Hubble Space Telescope does the same. The Very Large Telescope Array in Chile starts nightly monitoring. Scientists want spectroscopic data, chemical composition analysis, thermal measurements. This represents a unique opportunity. With Oumuamua, astronomers got caught flat-footed. The object was already leaving when they realized what they had. Comet Borisov gave them more time, but it remained relatively far from Earth throughout its passage. 3I/Atlas offers better geometry, closer approaches to multiple planets, more time to observe before perihelion, a wealth of data collection opportunities. Early observations reveal intriguing details. The object's trajectory aligns remarkably closely with the ecliptic plane. The angle of inclination measures just 5 degrees. Most objects entering the solar system arrive from random directions. They can plunge down from above the ecliptic, sweep up from below, or approach from any angle in between. The chances of threading directly along the planetary plane are astronomically low. Several astronomers note this coincidence publicly. Academic papers start using phrases like statistically unlikely and requires explanation. The object's velocity also stands out, 58 kilometers per second relative to the Sun. Oumuamua clocked in around 26 kilometers per second. Comet Borisov traveled at roughly 32 kilometers per second. 3I/Atlas is moving significantly faster than either predecessor. That velocity hints at a different origin point, possibly from a star system much farther away, or one moving at higher velocity relative to our local stellar neighborhood. September 7th, the James Clerk Maxwell Telescope in Hawaii captures detailed spectroscopic data. They detect hydrogen cyanide emissions. Production rate calculated at roughly 1.5 times 10 to the 25th molecules per second. A week later, September 14th, they observe again. The production rate has tripled, 4.5 times 10 to the 25th molecules per second. That equals about 2 kilograms of cyanide gas every second. The coma has expanded dramatically, now measuring 180,000 kilometers across. Asymmetric in shape, elongated along the anti-solar direction. A visible dust tail extends 50 arc-seconds, corresponding to approximately 100,000 kilometers. The comet's brightness has increased to apparent magnitude 14.2, still too faint for amateur telescopes, but well within reach of medium-sized professional instruments. Scientists begin comparing 3I/Atlas to its two predecessors in earnest. Oumuamua remains the most mysterious. Reddish color, tumbling rotation, cigar-shaped profile, anomalous acceleration, no visible coma or tail, completely unlike any comet or asteroid from our solar system. Comet Borisov sits at the opposite extreme. Perfectly normal comet behavior, chemical composition matching solar system comets almost exactly. Textbook example of what interstellar comets should look like. 3I/Atlas falls somewhere in between. It has a coma and tail like a proper comet. It's outgassing actively. But something feels off. The spectroscopic ratios don't quite match expectations. The object appears unusually rich in carbon dioxide compared to water. Most comets show the opposite pattern. Water dominates, with carbon dioxide as a minor component. Here, the proportions are flipped. The Very Large Telescope in Chile begins systematic observations focusing on minor chemical species. They detect cyanide gas, as expected, carbon monoxide, also expected. Then they find atomic nickel vapor. That raises eyebrows immediately. Nickel appears in comet spectra occasionally, but usually at very low levels. 3I/Atlas is pumping out nickel vapor at concentrations similar to the most active nickel-emitting comets ever observed. Some scientists view this as merely interesting. Others find it genuinely puzzling. Nickel typically remains locked in solid grains within the comet nucleus. Releasing significant amounts into the coma requires either extremely high temperatures or unusual chemical processes. October 3rd, 2025. 3I/Atlas makes its closest approach to Mars. Distance of just 0.19 astronomical units, roughly 28 million kilometers. That's closer than Mercury ever gets to Earth. The European Space Agency's ExoMars Trace Gas Orbiter swings into action. Its color and stereo surface imaging system, called CASIS, wasn't designed for comet observations. The camera normally photographs the Martian surface. Comets are roughly 50,000 times fainter than typical CASIS targets, but engineers quickly reprogram the system. They set exposure times to 5 seconds, maximum sensitivity. The spacecraft turns away from Mars and points toward the approaching comet. CASIS captures multiple images as 3I/Atlas crosses the Martian sky. The coma appears clearly in the processed data, elongated, asymmetric, glowing softly against the black background of space. Scientists eagerly await detailed analysis of these images. From Mars, the comet reached an apparent magnitude around 11, bright enough to observe clearly despite the imaging challenges. NASA's Mars Reconnaissance Orbiter also attempts observations. Its high-rise camera can resolve objects down to a few meters across on the Martian surface. Pointed at the comet, it captures the coma structure in unprecedented detail. Streams and filaments within the coma become visible, dust jets emanating from the nucleus, asymmetries suggesting active regions on the rotating nucleus surface. These close-range observations from Mars orbit provide data quality impossible to achieve from Earth. Astronomers start comparing the images to models of cometary activity. They look for signs of nucleus rotation, outburst events, fragmentation, any indication the object is breaking apart or behaving unusually. Back on Earth, Avi Loeb is watching all of this unfold with growing interest. He's been tracking 3I/Atlas since the discovery announcement, reading every paper, examining every spectrum, downloading raw data from public archives and running his own analyses. The more he studies this object, the more certain details bother him. The trajectory alignment with the ecliptic, that's statistically improbable for a random interstellar visitor. The close pass by Mars could be coincidence, but combined with the trajectory alignment, It suggests purposeful navigation. The gas envelope without corresponding trajectory perturbations. Comets wobble when they outgas. This one flies straight as an arrow. The unusual chemical composition. Why so much carbon dioxide? Why such strong nickel emissions? None of these details proves anything individually, but taken together, they form a pattern that nags at Loeb's scientific intuition. He starts making calls. Colleagues at other institutions, former students now working at observatories around the world. He asks them to prioritize specific measurements. High-resolution spectroscopy across multiple wavelengths. Detailed photometry to track any variations in brightness. Polarimetry to analyze the dust properties. Radio observations to detect any unexpected emissions. Loeb knows he's walking a thin line. His reputation took hits after the Oumuamua controversy. Many colleagues respect his astrophysics work, but consider his alien spacecraft hypothesis too speculative, unscientific, attention-seeking. He risks further professional marginalization by pursuing this again. But Loeb believes the data will speak for itself eventually. If 3I/Atlas truly represents a natural comet, the observations will prove that conclusively. If something more unusual is happening, the evidence will emerge through careful, systematic study. By mid-October, Loeb has compiled enough data to formulate his argument. He identifies 6 specific characteristics that, in his assessment, merit serious consideration of non-natural explanations. He's not claiming definitive proof. He's arguing that the null hypothesis, assuming this is an ordinary comet, faces significant challenges. The scientific method requires testing hypotheses against observations. If observations don't fit the expected pattern, you must either modify your hypothesis or consider alternatives. Loeb believes the alternative hypothesis, artificial origin, deserves a place at the table. He prepares a detailed technical paper outlining his reasoning. 6 main points, supporting data for each, quantitative analysis wherever possible. He submits the paper to the Astrophysical Journal. Simultaneously, he decides to go public. Better to present his case directly than let it leak through rumors and mischaracterizations. He schedules interviews with science journalists, prepares a press release, braces for the inevitable backlash from colleagues who view this as reckless speculation. The astronomical community is about to split into camps again. Team natural origin versus team artificial origin. Most scientists will land firmly in the first camp. They'll argue every observation has a plausible natural explanation. Yes, the trajectory alignment is unlikely, but unlikely events happen. Yes, the chemical composition is unusual, but comets show enormous diversity. Yes, the outgassing pattern is strange, but our models of cometary activity remain incomplete. They'll dismiss Loeb's arguments as cherry-picking anomalies while ignoring the simpler explanations. A smaller group will remain genuinely uncertain. They'll acknowledge Loeb raises valid questions while stopping short of endorsing his conclusions. They'll call for more data, better observations, careful analysis before drawing firm conclusions. And a tiny minority will find Loeb's case compelling enough to consider seriously. They won't necessarily agree with him, but they'll admit the possibility deserves investigation rather than immediate dismissal. The debate is about to intensify dramatically as 3I/Atlas approaches perihelion and the quality of observational data reaches its peak. October 18, 2025. The Keck Observatory in Hawaii releases new spectroscopic data that sends ripples through the astronomy community. The images reveal something nobody anticipated. 3I/Atlas is releasing nickel vapor at a rate of 4 grams per second. 4 grams might sound trivial, but sustained over hours and days, that adds up to enormous quantities. More significantly, the nickel appears isolated. Normally in comets, nickel and iron appear together in roughly equal proportions. They're chemically bonded in the parent minerals that make up cometary nuclei. When those minerals vaporize, both elements should appear in the gas simultaneously. But the Keck spectra show abundant nickel with essentially no iron signature. That's genuinely weird. The team identifies the compound as nickel tetracarbonyl. That's nickel bonded to 4 carbon monoxide molecules. On Earth, we produce nickel tetracarbonyl industrially. It's part of a refining process called the Mond process, invented in 1890. You pass carbon monoxide gas over impure nickel. The reaction creates nickel tetracarbonyl vapor, which you can then separate and decompose to yield pure nickel metal. The aerospace industry uses this refined nickel extensively. High-strength alloys for jet engines, corrosion-resistant coatings for spacecraft, structural components for satellites. Finding nickel tetracarbonyl in a comet is unprecedented. Avi Loeb immediately recognizes the significance. He tells journalists that this compound has only been observed previously in industrial contexts. Nature doesn't typically produce it. Could there be some unknown natural process generating it? Possibly. But Loeb argues you need to consider the simpler explanation. If something looks like an industrial product and behaves like an industrial product, maybe it actually is an industrial product. The skeptics push back hard. Michelle Bannister, a planetary astronomer at the University of Canterbury in New Zealand, points out that comets are chemically complex objects. We've only studied a tiny fraction of the comets in our solar system up close. Interstellar comets formed under completely different conditions, different temperatures, different pressures, different chemical environments. We shouldn't be surprised when they show unexpected compositions. The nickel tetracarbonyl could result from unusual chemistry happening on the nuclear surface or within the coma. Carbon monoxide is clearly present in abundance. If metallic nickel particles are being released and interacting with carbon monoxide in the coma environment, maybe they spontaneously form the tetracarbonyl compound through natural photochemical reactions. Bannister argues we need to exhaust all natural explanations before jumping to artificial origin hypotheses. Extraordinary claims require extraordinary evidence. Right now we have unusual chemistry, but unusual isn't the same as impossible. Loeb counters by laying out his full argument systematically. He's compiled 6 distinct characteristics that collectively create a pattern worth serious attention. Let's walk through them carefully because each one builds on the previous. The first characteristic involves the trajectory geometry. When 3I/Atlas entered the solar system, its path aligned remarkably closely with the ecliptic plane. That's the flat disk where all 8 planets orbit. If you could look at the solar system edge-on, you'd see the planets moving roughly along a single line. Small deviations exist. Mercury tilts 7 degrees. Pluto goes way off at 17 degrees, but Pluto's planetary status remains contentious anyway. The major planets all stay within a few degrees of the ecliptic. Now picture an interstellar object approaching from the void. It could arrive from any direction. 360 degrees of azimuth, 90 degrees of elevation above the ecliptic, 90 degrees below. That's a full 4 pi steradians of solid angle coverage. The ecliptic plane represents an infinitesimally thin slice through that enormous possibility space. Yet 3I/Atlas threaded that needle. Its orbital inclination measures just 5.1 degrees. That puts it closer to the ecliptic than most asteroids in the main belt. Loeb calculates the probability of this happening randomly. The numbers come out to roughly 1 in several thousand. Not impossible, but improbable enough to raise questions. If you're designing a probe to survey planetary systems, aligning with the planetary plane makes perfect sense. You maximize your chances of encountering interesting targets. Earth probes do exactly this when exploring the outer solar system. Voyager, Cassini, New Horizons all stayed close to the ecliptic because that's where the interesting objects live. The second characteristic amplifies the first. 3I/Atlas didn't just align with the ecliptic abstractly, it passed extremely close to Mars on October 3rd, distance of roughly 0.19 astronomical units. That's closer than Venus ever approaches Earth. Loeb emphasizes the compound improbability. First, align with the ecliptic plane. Second, time your passage to intersect Mars's orbital path when Mars actually occupies that location. Mars takes 687 days to complete one orbit. 3I/Atlas had to arrive at precisely the right moment to achieve a close encounter. The orbital mechanics experts at NASA actually ran simulations. If you generate random interstellar trajectories through the solar system, what fraction produces close Mars encounters? The answer hovers around 1 in 10,000. Again, possible but unlikely. Loeb argues this could represent a deliberate gravity assist maneuver. Spacecraft routinely use planetary flybys to alter trajectories. The Voyager probes used Jupiter, Saturn, Uranus, and Neptune sequentially. Each encounter modified the velocity vector and aimed the probe toward the next target. If 3I/Atlas wanted to survey the inner solar system after approaching from interstellar space, a Mars flyby would provide useful trajectory control. You could use Mars's gravity to slow down slightly, adjust your inclination, fine-tune your perihelion distance, exactly what a prudent mission planner would do. Critics respond that close planetary encounters happen more often than Loeb suggests. Comet Siding Spring passed just 87,000 miles from Mars in 2014. Comet Shoemaker-Levy 9 actually impacted Jupiter in 1994. The solar system is a chaotic, dynamic environment. Objects pass near planets regularly. Cherry-picking one close encounter and declaring it evidence of intentional navigation represents confirmation bias. You're finding patterns in noise. Loeb replies that context matters. Siding Spring and Shoemaker-Levy originated within the solar system. Their orbits evolved over millions of years through gravitational interactions that naturally increased encounter probabilities. 3I/Atlas arrived from outside with no prior orbital evolution. It showed up already aligned with the ecliptic, already on a trajectory intersecting Mars. That's the difference between rolling dice repeatedly until you get lucky versus getting lucky on your first roll. The third characteristic focuses on outgassing behavior. behavior. Comets are messy objects when they approach the sun. Solar radiation heats the nucleus surface. Ices sublimate directly from solid to gas. Water, carbon dioxide, carbon monoxide, methane, ammonia, all transform into vapor. These gases carry dust particles along, creating the visible coma and tail. But the outgassing isn't uniform. The nucleus rotates. Different regions face the sun at different times. Some areas contain more volatile ices than others. The result is jets of gas shooting out from specific active regions. These jets act like tiny rocket engines. They push the comet around. Astronomers can actually see this effect directly in trajectory calculations. When you model a comet's path using pure gravitational physics, accounting for the sun and planets, your prediction won't quite match observations. The comet deviates slightly from the calculated orbit. Those deviations correlate with outgassing activity. More outgassing equals bigger deviations. Scientists call these deviations non-gravitational accelerations. Every active comet exhibits them to some degree, except 3I/Atlas apparently doesn't. Multiple teams have now calculated its orbit using months of positional data. The gravitational model fits beautifully. No significant non-gravitational terms required. The comet possesses an obvious coma. Spectroscopy confirms active outgassing. Water, carbon dioxide, carbon monoxide, cyanide, nickel tetracarbonyl, all streaming off the nucleus. Yet the trajectory remains purely gravitational. That's the equivalent of firing a rocket engine while maintaining perfectly straight-line motion. Physically possible only if you have another engine firing in the opposite direction to cancel out the thrust. Loeb suggests this indicates active stabilization. The object is compensating for outgassing forces in real time to maintain its intended trajectory. That requires sensors to detect perturbations and thrusters to counteract them. Natural comets lack those capabilities. They tumble chaotically. Their outgassing patterns change unpredictably as different regions activate and deactivate. They wobble and deviate. 3I/Atlas flies like it's on rails. Critics propose alternative explanations. Maybe the nucleus is unusually large and massive. Small outgassing forces wouldn't perturb a big enough object significantly. Maybe the rotation axis points directly toward or away from the sun. That geometry could produce symmetric outgassing with minimal net thrust. Maybe the active regions are positioned such that their jets naturally cancel out. These scenarios require specific configurations, but they're physically plausible. Loeb acknowledges these possibilities while noting they also represent low probability situations. At some point, when you need multiple unlikely conditions to explain observations, you should consider whether your baseline hypothesis might be wrong. The fourth characteristic concerns physical dimensions. Early estimates based on brightness and assumptions about surface reflectivity suggested a nucleus diameter up to 20 kilometers. That would make 3I/Atlas enormous by cometary standards. Comet Hale-Bopp, one of the largest comets ever observed, measures roughly 60 kilometers across. Halley's comet spans about 15 kilometers. Most comets are much smaller, typically a few kilometers at most. A 20-kilometer interstellar comet would be truly exceptional. Subsequent observations refined these estimates downward. The Hubble Space Telescope obtained high-resolution images in August. Analysis suggests the nucleus diameter probably falls below 5 or 6 kilometers, possibly as small as 320 meters. That's still respectable size, but not extraordinarily large. However, mass estimates remain uncertain. Brightness tells you about surface area and reflectivity. It doesn't directly reveal mass, which depends on density. Is the nucleus solid ice, porous ice mixed with rock, hollow? We simply don't know. Mass matters for the outgassing question. A very massive object would indeed resist non-gravitational perturbations better. But estimating mass requires observing the comet's gravitational influence on other objects, and nothing has passed close enough for that measurement. Loeb argues the size issue connects to another puzzle. How did such a large object survive intact through billions of years of interstellar travel? Space isn't empty. Dust grains, hydrogen atoms, radiation fields all erode surfaces gradually. Close passes by stars create tidal stresses that can fragment objects. The longer you drift through the galaxy, the more abuse you take. Large, fragile structures shouldn't survive. Either 3I/Atlas is younger than it appears, or it's built more robustly than natural comets typically are. The fifth characteristic brings us back to chemistry. Beyond the nickel tetracarbonyl issue, other compositional oddities have emerged. The carbon dioxide to water ratio appears inverted compared to most comets. Typically, water dominates cometary ice composition. Carbon dioxide exists as a minor component, maybe 10 to 20% by abundance. 3I/Atlas shows the opposite pattern. Carbon dioxide clearly dominates the outgassing. Water is present but subdued. Only a handful of comets in our solar system exhibit this chemistry, and they're considered unusual. Some scientists hypothesize these carbon dioxide-rich comets formed in the outer regions of the planetary disk beyond Neptune's orbit, where temperatures were cold enough to preferentially condense carbon dioxide. Interstellar space is even colder. Maybe 3I/Atlas formed under extreme cold conditions that favored carbon dioxide retention over water. That's plausible. But combined with the nickel tetracarbonyl detection, the unusual carbon dioxide abundance, the lack of iron paired with nickel, the whole chemical picture starts looking strange. Loeb notes that aerospace alloys often use nickel for strength and carbon-based composites for lightweight structural applications. Carbon dioxide could theoretically be used as a propellant or coolant in certain spacecraft designs. He's not claiming the chemistry proves artificial origin. He's pointing out that if you were engineering an interstellar probe, these materials wouldn't be unreasonable choices. The sixth and final characteristic involves what comes next. 3I/Atlas hasn't left yet. Perihelion occurs around October 30th. After that, the object will swing past Venus at a relatively safe distance, then make an awkward approach to Earth with the Sun blocking our view, then head toward the outer solar system. Current trajectory models predict it will reach Jupiter's orbit in early 2026 and Saturn's orbit by late 2027. Then it exits into interstellar space. But models are predictions, and predictions can be wrong. Loeb points out that if this object possesses maneuvering capability, we might see course corrections during the outbound leg. Small velocity changes compound over time into large trajectory alterations. A delta V of just a few meters per second applied near Jupiter could redirect the object significantly, maybe toward the inner solar system for another pass, maybe toward a different target we haven't considered. The key point is we need to keep watching. If 3I/Atlas suddenly deviates from the predicted path in a way that gravity and outgassing can't explain, that would constitute compelling evidence of active control. Alternatively, if it follows the gravitational trajectory perfectly through 2028 and beyond, the natural origin hypothesis gains strong support. Loeb is essentially proposing a test. Keep observing. Let the data decide. The scientific community splits into distinct camps as Loeb's analysis circulates through research networks. Most astronomers land firmly on the natural origin side. They acknowledge the observations are intriguing, but insist every anomaly has a plausible explanation within conventional physics and chemistry. The trajectory alignment, while statistically unlikely, falls within the realm of random chance. Roll enough dice and eventually you'll see improbable patterns. The Mars flyby timing represents another statistical coincidence. Thousands of objects pass through the solar system over geological timescales. Some will inevitably experience close planetary encounters purely by chance. The lack of non-gravitational acceleration could stem from symmetric outgassing patterns, or a nucleus large enough that tiny jets produce negligible perturbations. The unusual chemistry reflects formation conditions in a different stellar environment. We've studied perhaps 24 comets in detail out of trillions that exist. Expecting every comet to match our limited sample represents hubris. The nickel emissions, while noteworthy, appear in other comets, including Comet Borisov. Nickel tetracarbonyl formation could occur through photochemistry we haven't fully characterized yet. Each individual piece of evidence admits a natural explanation. String them together and you still have a comet, just an unusual one. A smaller contingent occupies the uncertain middle ground. These researchers acknowledge Loeb raises legitimate questions while stopping short of endorsing his conclusions. They emphasize the importance of gathering more data before drawing firm conclusions. Science advances through observation and hypothesis testing, not premature declarations. We need spectroscopic measurements at higher resolution, detailed photometry to search for periodic variations indicating nucleus rotation, thermal infrared observations to estimate surface temperatures and constrain nucleus size, radio observations searching for any unexpected emissions, perhaps polarimetry to analyze dust grain properties in the coma. These measurements will either confirm the natural comet hypothesis definitively or reveal additional anomalies requiring explanation. Until we've exhausted observational possibilities, declaring victory for either side seems premature. The scientific method demands patience and rigor. Extraordinary claims do require extraordinary evidence, but dismissing unusual observations without thorough investigation represents equally poor science. Then there's the tiny minority who find Loeb's argument genuinely compelling. They don't necessarily believe 3I/Atlas is an alien spacecraft with high confidence. They simply argue the hypothesis deserves serious consideration rather than reflexive dismissal. Science history overflows with examples where maverick ideas eventually proved correct. Heliocentrism, plate tectonics, the bacterial origin of peptic ulcers, the existence of dark matter, the acceleration of cosmic expansion. Everyone faced fierce initial resistance. The scientific establishment mocked the proposers. Critics demanded impossible standards of proof. Yet eventually, accumulating evidence forced the paradigm shift. These researchers worry that automatic rejection of unconventional explanations, particularly regarding potential extraterrestrial technology, reflects sociological bias more than objective evaluation. The academic culture strongly disincentivizes speculation about alien civilizations. Researchers who venture into this territory risk their reputations and career advancement. Journals hesitate to publish papers proposing artificial explanations for astronomical observations. Funding agencies rarely support such research. The result is a systematic blind spot. We claim to search for extraterrestrial intelligence through SETI radio surveys, yet reflexively dismiss potential physical artifacts when they appear in our solar system. That asymmetry deserves examination. Vladimir Surdin offers perhaps the most balanced philosophical perspective on the entire controversy. He's watched scientific debates play out over decades, seen passionate arguments on both sides of countless issues, observed how consensus shifts as new data arrives. His view emphasizes humility and open-mindedness balanced with healthy skepticism. Yes, Loeb's hypothesis is speculative. Yes, natural explanations exist for each observation, but science advances by testing speculative ideas against reality, not by declaring certain topics off-limits. If Loeb is correct, he becomes a hero who recognized something everyone else missed. If he's wrong, the scientific community moves forward, having thoroughly investigated an interesting possibility. Either outcome advances knowledge. The worst response would be refusing to look seriously at the evidence because the hypothesis makes us uncomfortable. Surdin notes that Loeb isn't some fringe conspiracy theorist. He's a legitimate astrophysicist with expertise directly relevant to this question. His arguments deserve evaluation on their technical merits, not dismissal based on their implications. Treat the hypothesis as you would any other scientific proposal. What predictions does it make? What observations would confirm or refute it? Design tests and gather data. Let evidence guide conclusions rather than preconceived notions about what seems plausible. The debate intensifies as October progresses. More observatories join the observation campaign. The Keck Observatory in Hawaii obtains high-resolution spectra showing detailed chemical profiles. The Atacama Large Millimeter Array in Chile measures molecular emissions at radio wavelengths. The Hubble Space Telescope captures the sharpest images yet of the comet's inner coma structure. Ground-based networks coordinate simultaneous observations to track rapid changes in activity level. Amateur astronomers contribute valuable data using backyard telescopes. The Minor Planet Center receives hundreds of astrometric measurements daily, refining the orbital solution to remarkable precision. Scientists can now predict the comet's position months in advance, with uncertainty measured in kilometers rather than thousands of kilometers. These intensive observations reveal additional peculiarities that fuel further debate. The Keck data shows the nickel emission varies with a period of roughly 8 hours. That suggests nucleus rotation with active regions that face toward or away from the sun as the comet spins. Perfectly normal behavior for a comet, but the cyanide emission shows a different periodicity, around 11 hours. How can two different gases outgassing from the same rotating nucleus show different periods? Either the nucleus has an extremely irregular shape causing complex viewing geometry effects, or the active regions emitting nickel and cyanide are located at different latitudes with different effective rotation periods, or something more unusual is happening. Researchers propose several models to explain the discrepancy. None fits perfectly. The question remains unresolved. The Hubble images show a subtle asymmetry in the inner coma. Material appears slightly more concentrated on one side of the nucleus than the other. Computer models of cometary outgassing predict roughly symmetric comas, unless the nucleus is rotating with its pole pointed nearly toward the sun, or unless multiple jets are firing from different locations at varying intensities. Determining which scenario applies requires knowing the rotation axis orientation, which remains uncertain. Attempts to detect periodic variations in the comet's overall brightness have so far failed. Either the nucleus is nearly spherical, showing minimal variation as it rotates, or the rotation period is long enough that we haven't observed a complete cycle yet, or the viewing geometry is unfavorable. More data is needed. Radio observations from ALMA detect carbon monoxide emission lines with surprising width. Spectral line width indicates velocity. Wider lines mean molecules moving faster. For thermal emission, line width relates to temperature, but the measured widths suggest temperatures higher than expected for simple sublimation from a sunlit surface. Something is accelerating the carbon monoxide molecules beyond thermal velocities. Possible explanations include exothermic chemical reactions in the coma, collisional processes where fast-moving dust particles transfer momentum to gas molecules, or expansive acceleration as high-pressure gas escapes from subsurface voids. All three mechanisms operate in normal comets to varying degrees, but quantitative modeling hasn't yet explained the observed velocities completely. Another puzzle for theorists to solve. Amateur astronomers monitoring the comet's brightness report an unexpected surge on October 12th. The apparent magnitude jumped from 14.2 to 13.6 over roughly 6 hours, then gradually faded back to baseline over the next 2 days. That corresponds to the comet temporarily brightening by about 50%. Such outbursts are well documented in comets. They typically result from sudden exposure of fresh ice as chunks of surface crust break off, or from subsurface pockets of volatile material suddenly breaching to the surface and rapidly vaporizing. Comet 17P/Holmes famously brightened by a factor of 500,000 in just 42 hours during its 2007 outburst, becoming briefly visible to the naked eye despite normally being a faint telescopic object. By comparison, 3I/Atlas's mini-outburst is minor, but Loeb seizes on the timing. The outburst occurred when the comet was approximately 1.9 astronomical units from the Sun. Solar heating at that distance should be relatively stable. What triggered the sudden activity change? Natural fracturing of surface ice is plausible, but Loeb suggests the alternative, that the object activated some internal process, perhaps testing systems in preparation for perihelion passage. Critics respond that you can explain anything if you allow yourself to invoke unspecified internal processes. That's not falsifiable. Science requires testable predictions. Loeb counters that he's not proposing an untestable model. If 3I/Atlas is artificial, we should see evidence of controlled behavior, trajectory corrections during the outbound leg, radio emissions if it attempts communication, structured variations in brightness suggesting artificial components reflecting sunlight, anomalous thermal signatures inconsistent with simple ice sublimation. He's proposing observations that would distinguish between hypotheses. Natural comets behave in well-characterized ways. Artificial probes would display different patterns. Watch and measure. The data will reveal the truth. By late October, 3I/Atlas approaches perihelion. The comet brightens to apparent magnitude 12.8, just below the threshold of amateur binocular visibility from dark sky locations. The coma has expanded to nearly 300,000 kilometers across, roughly equivalent to the distance between Earth and the Moon. The dust tail stretches 4 degrees across the sky, or about 8 times the apparent diameter of the full Moon. Of course, the tail is extremely diffuse. It appears only in long-exposure photographs. To the human eye, even through a telescope, the comet looks like a faint fuzzy blob with perhaps a hint of elongation in one direction. Veteran comet observers rate it as moderately impressive, brighter than most comets but nowhere near great comets like Hale-Bopp or Hyakutake that dominated evening skies in the 1990s. Perihelion occurs on October 30th at precisely 14 hours 23 minutes universal time. The comet reaches its closest point to the Sun at 1.398 astronomical units. That's roughly 209 million kilometers, or about 130 million miles. For comparison, Earth orbits at 1 astronomical unit, and Mars orbits at roughly 1.5 astronomical units. So 3I/Atlas passes between Earth's orbit and Mars's orbit, slightly closer to Mars. The geometry is unfortunate for Earth-based observers. The comet lies nearly in line with the Sun as seen from Earth. Solar glare makes observations challenging despite the comet's increased brightness. The best views come from spacecraft positioned at different vantage points. NASA's stereo satellites, designed to observe the Sun from locations ahead of and behind Earth in its orbit, have clear views of the comet near perihelion. They capture images showing the coma and tail in exquisite detail against the black background of space. Scientists watch intently for any unexpected behavior during perihelion passage. Comets sometimes fragment when approaching close to the Sun. Tidal forces and rapid heating create stresses that can crack weakened nuclei. Comet Shoemaker Levy 9 famously broke into more than 20 pieces before impacting Jupiter in 1994. Comet Linear fragmented spectacularly in 2000, transforming from a single object into a cloud of debris. Comet Ison disintegrated entirely during its perihelion passage in 2013, approaching within 1.2 million miles of the Sun's surface. If 3I/Atlas were a loosely bound rubble pile, perihelion might destroy it. Instead, the comet survives intact. No signs of fragmentation appear in any images. The brightness increases smoothly as solar heating intensifies, then begins decreasing gradually as the comet moves away from perihelion. Exactly the behavior expected for a structurally sound nucleus. Whether that nucleus consists of natural ice and rock or something more exotic remains the question. While the astronomical community debates 3I/Atlas, Avi Loeb hasn't been sitting idle. After the Oumuamua controversy, he launched an ambitious project to search historical records for other potential interstellar visitors we might have missed. The premise is straightforward. If interstellar objects pass through the solar system occasionally, some must have collided with Earth over the decades. Meteorites rain down constantly. Most burn up harmlessly in the atmosphere. A few survive to impact the ground. Scientists have been cataloging these events systematically since the early 20th century. Modern sensor networks detect fireballs globally. Satellites track atmospheric entries. Military early warning systems designed to spot missile launches also catch bright meteors. The data exists. Loeb's team just needed to dig through it looking for anomalies. They focused on velocity as the primary discriminator. Objects orbiting the Sun can't exceed escape velocity without additional energy input. For Earth's location, solar escape velocity equals roughly 42 kilometers per second. Add Earth's orbital velocity of 30 kilometers per second, and you get an upper limit around 72 kilometers per second for objects approaching head-on. Meteorites arriving faster than this threshold must originate from outside the solar system. The team combed through US government sensor data, academic fireball networks, and amateur observer reports. They found 3 candidates showing hyperbolic trajectories with entry speeds exceeding 80 kilometers per second. 2 remain unconfirmed due to insufficient data. The third case appears solid. January 8, 2014. A meteor blazed across the sky northeast of Papua New Guinea. Multiple sensors triangulated its trajectory. Entry velocity measured at roughly 60 kilometers per second relative to Earth. But Earth was moving at 30 kilometers per second in its orbit at that moment. Vector addition gives you a heliocentric velocity exceeding solar system escape speed. The object came from interstellar space. It measured perhaps half a meter across, tiny compared to Oumuamua or 3I/Atlas, but genuinely interstellar. The meteor exploded approximately 19 kilometers above the ocean's surface, releasing energy equivalent to several tons of TNT. Fragments rained down into the water, scattering across several square kilometers of seafloor. Loeb became obsessed with recovering those fragments. Physical samples would provide definitive proof of interstellar origin and enable detailed compositional analysis, but the Pacific Ocean floor at that location sits roughly 3 kilometers deep. The search area spans several square kilometers. Finding small metallic fragments in that environment approaches needle-in-haystack difficulty. Loeb needed funding, specialized equipment, and a team willing to attempt something most colleagues considered quixotic at best. He approached wealthy donors who'd supported his research previously. Some declined. Others found the idea intriguing enough to contribute. By mid-2023, Loeb had raised sufficient funds to charter an oceanographic research vessel called the Silver Star. The expedition launched in June 2023. The ship carried a customized magnetic sled designed to detect and collect metallic particles from the seafloor. They towed the sled behind the vessel in a systematic search pattern, covering the predicted debris field methodically. The magnetic collection yielded hundreds of tiny spherules, most smaller than a millimeter across. Back in laboratory facilities, Loeb's team analyzed the samples using electron microscopy, mass spectrometry, and other sophisticated techniques. The composition surprised them. High nickel content, unusual isotope ratios for several elements, including iron, magnesium, and aluminum. The isotopic signatures didn't match any known terrestrial sources. They also differed from typical meteorites originating within the solar system. Loeb published preliminary results in late 2023, claiming the spherules represent fragments of an interstellar meteor. The material's composition suggests formation in an environment quite different from the early solar nebula that birthed our planets. Perhaps a supernova remnant where unusual nuclear processes created exotic isotope ratios, or material processed through multiple stellar generations, accumulating chemical signatures reflecting complex galactic recycling. Loeb also noted some spherules contain microstructures resembling manufactured alloys, grain boundaries suggesting controlled solidification, crystal orientations hinting at directional cooling processes. He stopped short of claiming definitive proof of alien technology, but argued the data merits serious consideration of that possibility. Critics attacked the work from multiple angles. The recovery location sits along major shipping lanes. Decades of maritime traffic have scattered industrial debris across the seafloor. Spherules could easily be welding slag, corroded ship fragments, or other anthropogenic contamination. The unusual isotope ratios might reflect terrestrial industrial processes rather than interstellar origin. Maybe someone dumped processed metal waste overboard. Maybe military ordnance testing scattered exotic materials. Proving the spherules actually came from the 2014 meteor rather than some mundane source requires stronger evidence than Loeb has provided. Additionally, other meteoriticists examined the data and disputed the isotopic interpretations. They argued the measurements fall within known ranges for certain rare rare meteorite types. Solar system origin remains plausible. The debate continues with no clear resolution. Loeb maintains his position that the evidence supports interstellar origin and possibly artificial composition. Skeptics insist natural explanations remain adequate. Both sides await additional data that might settle the question definitively. Meanwhile, Loeb has continued the search. He's planning another expedition to recover more samples and hopes to find larger fragments that survived atmospheric entry intact. The controversy has done little to diminish his determination. If anything, the criticism seems to energize him. He views scientific consensus not as truth, but as provisional agreement subject to revision when new evidence emerges. His role, as he sees it, involves challenging that consensus when observations don't fit prevailing models. Which brings us back to 3I/Atlas and the broader question of how science should respond to anomalous data. Do we default to conventional explanations even when they require multiple unlikely conditions, or do we seriously consider unconventional possibilities when patterns emerge that challenge our assumptions? These philosophical questions have practical implications for how we search for life and intelligence beyond Earth. For decades, SETI projects have scanned radio frequencies hoping to detect artificial signals from distant civilizations. Those efforts rest on the assumption that advanced technology produces recognizable signatures we can identify remotely. Yet when potential physical artifacts appear in our own solar system, we reflexively dismiss artificial origin hypotheses. That asymmetry deserves examination. Perhaps we're looking for extraterrestrial intelligence in the wrong places, or using overly narrow criteria. Let's shift gears completely now and talk about something we promised at the beginning: Mars, the search for life in our solar system. Because while we debate whether 3I/Atlas might be a spacecraft, we have solid evidence that Mars once hosted conditions suitable for life. Maybe life actually emerged there. Maybe it still exists in subsurface environments protected from the harsh surface conditions. The story of how we discovered Mars's watery past represents one of the great scientific achievements of the space age. But that story begins with a massive mistake, a collective delusion that gripped astronomy for decades. 1877, Italian astronomer Giovanni Schiaparelli observes Mars during a particularly favorable opposition when the planet approaches closest to Earth. He's using an 8.7-inch refractor telescope at Milan's Brera Observatory. The seeing conditions are excellent. Schiaparelli sketches detailed maps of the Martian surface, noting various dark and light regions. He also draws linear features connecting some of these regions. He calls them canali, an Italian word meaning channels. The term doesn't necessarily imply artificial construction. Rivers are channels. Natural valleys are channels. Schiaparelli simply describes linear features he observes through his telescope. His maps gain international attention. Other astronomers attempt to confirm the observations. Some see similar linear patterns, others see nothing definite. Then along comes Percival Lowell, a wealthy American businessman fascinated by astronomy. Lowell reads Schiaparelli's reports and becomes convinced the canali represent artificial constructions built by Martian civilization. He establishes a private observatory in Flagstaff, Arizona, specifically to study Mars. The location offers excellent seeing due to high altitude and stable atmospheric conditions. Lowell spends years observing Mars meticulously, drawing elaborate maps showing hundreds of linear canals crisscrossing the planet. He publishes books arguing these canals represent a planet-wide irrigation system constructed by an advanced but dying civilization desperately trying to transport water from polar ice caps to equatorial agricultural regions. His theories capture public imagination. Newspapers run stories about Martian engineers. Science fiction authors incorporate Lowell's ideas into stories about ancient Martian empires. The canals become accepted fact in popular culture despite mounting skepticism from professional astronomers. Here's what actually happened. Human vision isn't perfectly objective. When you stare at a complex, low-contrast scene through a telescope, your brain tries to impose order on random patterns. Scattered dark patches become connected lines. The eye naturally seeks structure even when none exists. Schiaparelli and Lowell were observing real features on Mars, legitimate albedo variations caused by different surface materials. But they were connecting those features into linear patterns that existed primarily in their perception rather than on the planet itself. Other factors contributed to the illusion. The human eye contains blood vessels that cast shadows on the retina. Stare at a bright field through an eyepiece long enough, and you might start perceiving those internal vascular patterns as external features. Additionally, atmospheric turbulence creates transient distortions. A momentary alignment of seeing conditions might create the appearance of a straight line connecting two features. The observer notes it, searches for it again, and confirmation bias ensures they'll find something resembling that pattern. The canal controversy raged for decades. As telescopes improved and photographic techniques advanced, the canals became increasingly elusive. Early photographs of Mars showed no clear linear features. Loeb argued photographic emulsions lacked the sensitivity of the trained human eye. Visual observers continued reporting canals well into the 1960s. The question wasn't definitively settled until NASA's Mariner missions reached Mars. Mariner 4 flew past in July 1965, returning 22 grainy photographs. No canals. Mariner 6 and 7 followed in 1969 with higher resolution images. Still no canals. Mariner 9 entered orbit in November 1971 and mapped the entire planet systematically. The images revealed a geologically complex world with impact craters, volcanoes, canyons, and ancient river valleys, but absolutely zero evidence of artificial canals or any structures suggesting technological civilization. The lesson from this episode resonates today. Even trained observers using quality instruments can deceive themselves when expectations influence perception. Peer review and independent verification are essential. Extraordinary claims require extraordinary evidence, a principle Carl Sagan popularized decades later. The canal controversy also illustrates how cultural context shapes scientific interpretation. Lowell's theories emerged during an era of massive irrigation projects on Earth. The Suez Canal opened in 1869. Planning for the Panama Canal was underway. Engineers were reshaping landscapes through monumental public works. Projecting similar ambitions onto Mars seemed natural. We see the universe through lenses shaped by our technological capabilities and cultural preoccupations. That cognitive bias affects contemporary debates just as much as historical ones. After the Martian canals proved illusory, astronomers spent decades correcting their understanding of the red planet. The early Mariner missions painted a discouraging picture, a cold, dry desert world with a tenuous atmosphere providing barely 1% of Earth's surface pressure, temperatures plunging far below freezing, intense ultraviolet radiation bathing the surface. Early hopes for finding life faded quickly. Then Viking 1 and Viking 2 landed in 1976, carrying biology experiments specifically designed to detect microbial metabolism. Both landers scooped up soil samples and tested them for signs of life. The results came back ambiguous. Some experiments showed patterns consistent with biological activity. Others detected unusual chemistry that could be explained through non-biological processes. Scientists debated the findings for years. Eventually, the consensus settled on sterile soil. Mars appeared lifeless, at least on its surface where the Viking landers sampled. That conclusion hardened into dogma throughout the 80s and early 90s. Mars was dead, hostile to life, case closed. Then, in 1996, NASA scientists dropped a bombshell announcement. They'd been studying a meteorite recovered from Antarctica 12 years earlier. The rock, designated Allen Hills 84001 after its discovery location, originated from Mars. Impact events occasionally blast Martian rocks into space. Some of these meteorites eventually fall to Earth. Geochemical analysis proved ALH 84001's Martian origin definitively. The rock crystallized from molten lava about 4 billion years ago, making it one of the oldest known Martian samples. But age wasn't what made headlines. The research team led by David McKay found microscopic structures inside the meteorite that resembled fossilized bacteria. Tiny worm-like shapes measuring 20 to 100 nanometers long, organic molecules called polycyclic aromatic hydrocarbons, or PAHs, which on Earth often form when organisms decay, grains of magnetite and iron sulfide minerals, similar to those produced by certain bacteria, carbonate globules suggesting the rock once contained liquid water. McKay's team published their findings in the journal Science. The paper made careful, measured claims. The structures might represent evidence of ancient Martian life. The chemistry was consistent with biological processes. The features collectively formed a pattern worth serious consideration. President Clinton held a White House press conference about the discovery. He called it potentially one of the greatest discoveries in human history. The rock went on display at the Smithsonian. Media coverage exploded worldwide. Public excitement reached levels not seen since the Apollo moon landings. Finally, concrete evidence that we might not be alone. Then the backlash began. Other scientists examined the data critically. They found alternative explanations for each feature. The worm-like structures were too small to be complete cells. Terrestrial bacteria measure at least 200 nanometers. These Martian structures were smaller by an order of magnitude, too small to contain the molecular molecular machinery necessary for life as we understand it. Maybe they represented mineral formations that coincidentally resembled biological shapes. The PAH molecules could have formed through non-biological chemistry. Impacts generate high temperatures and pressures that create complex organics without life involvement. The magnetite and iron sulfide grains might precipitate from purely chemical reactions in water. The carbonate globules proved the rock once interacted with liquid water, but water alone doesn't prove life. By the early 2000s, most astrobiologists had concluded ALH 84001 didn't provide compelling evidence for Martian life. Suggestive, yes. Definitive, no. The structures remained ambiguous. Natural explanations seemed adequate, yet the debate never completely died. A minority of researchers continued arguing the biological interpretation remained viable. They pointed out that small size doesn't necessarily preclude life. Some terrestrial bacteria called ultramicrobacteria can survive in compressed states smaller than 200 nanometers. Ancient life might have been simpler and smaller than modern cells. The combination of features, all appearing together in the same rock, seemed difficult to explain through random chemistry. No consensus emerged. The question remains open decades later. Only returning the rock's parent material from Mars for detailed laboratory study will resolve the controversy definitively. That requires a sample return mission, which NASA and international partners are actively planning for the late 2020s or early 2030s. While scientists debated fossil microbes in meteorites, spacecraft continued orbiting Mars, and rovers explored the surface. These missions revealed something remarkable. Mars wasn't always the frozen desert we see today. Ancient Mars was warm and wet. The evidence became overwhelming as high-resolution cameras mapped the planet systematically. Networks of dried river channels snake across ancient terrain, delta formations where rivers once emptied into standing bodies of water, shoreline features marking ancient sea levels, layered sedimentary rocks formed in aqueous environments, clay minerals that only form in the presence of liquid water. The planet's entire northern lowlands, covering roughly a third of the Martian surface, sit at lower elevation than the southern highlands. The elevation difference and geographic distribution match what you'd expect for an ancient ocean basin. Scientists estimate that roughly 3.5 billion years ago, Mars possessed a substantial ocean covering much of its northern hemisphere. Water depth possibly reached hundreds of meters. The ocean persisted for perhaps hundreds of millions of years, long enough for complex chemistry to occur, long enough for life to emerge if conditions were favorable. What happened to all that water? Some evaporated and escaped to space. Mars's weak gravity and lack of a protective magnetic field allowed solar wind to strip away the atmosphere gradually. As atmospheric pressure dropped, liquid water became unstable. It either froze into ice locked in polar caps and subsurface permafrost, or sublimated directly from ice to vapor and escaped. The process took millions of years. It wasn't a sudden catastrophe, but a slow decline from a relatively hospitable world to the harsh environment we observe today. In 2023 and 2024, China's Zhurong rover explored a region called Utopia Planitia in the northern lowlands. The rover carried a ground-penetrating radar capable of imaging subsurface structures down to 80 meters depth. The radar revealed layered deposits consistent with ancient shoreline environments. Beach formations preserve characteristic stratification patterns, coarse sediments at the base grade into finer sediments higher up. Ripple marks frozen in stone indicate shallow water wave action. The Chinese team published detailed analysis showing multiple distinct layers representing different sea levels over time. Mars's ancient ocean didn't maintain constant depth. Climate variations caused water levels to fluctuate, just as ice ages on Earth alternately trap water in glaciers or release it to raise sea levels. These fluctuations created multiple beach terraces at different elevations, all preserved in the geological record. Finding conclusive evidence of an ancient ocean matters enormously for astrobiology. Life as we understand it requires liquid water. Organic chemistry functions best in aqueous solution where molecules can interact freely. The presence of a long-lived ocean dramatically improves the odds that life could have emerged on early Mars. But did it? And if Martian life existed 3 billion years ago, could it still survive today in protected subsurface refuges? Which brings us to the most exciting discovery announced just weeks ago. On September 10, 2025, NASA held a press conference to discuss a rock sample collected by the Perseverance rover. The rover has been exploring Jezero crater since February 2021. Jezero once contained a lake fed by an ancient river. The delta, where that river emptied into the lake, preserved sediments laid down layer by layer over long periods. Perfect environment for detecting biosignatures if Martian life ever existed. Perseverance carries sophisticated instruments capable of analyzing rock chemistry and searching for organic molecules. The rover also collects samples for eventual return to Earth, storing them in sealed tubes for future retrieval. Sample number 24 came from an area called Bright Angel. The rock shows distinctive banding with alternating light and dark layers. Chemical chemical analysis revealed high concentrations of organic compounds. But organic molecules alone don't prove life. They can form through non-biological processes. What made this rock extraordinary were features visible under the rover's magnifying camera. Small circular structures embedded in the rock, measuring roughly 1 millimeter across, rings of iron phosphate surrounding what appear to be hollow cores. On Earth, certain bacteria create similar structures during metabolic processes. The bacteria concentrate iron and phosphorus from their environment, forming mineral deposits around their cell walls. When the bacteria die and decay, these minerals preserve the shapes of the cells as microscopic fossils. The NASA team emphasized caution in their announcement. They're not claiming definitive proof of life. They're saying this rock represents the most compelling evidence yet discovered. The features collectively suggest biological activity more strongly than any previous Martian sample. Katie Stack Morgan, deputy project scientist for Perseverance, told journalists, "This is arguably the best evidence we have so far. The combination of organic molecules, distinctive mineral patterns, and morphological features consistent with fossilized bacteria creates a strong case. But strong isn't the same as proven. The researchers want to get this rock sample back to Earth, where they can analyze it with instruments far more powerful than anything a rover can carry. Electron microscopes, mass spectrometers, isotope analyzers, all the tools of modern analytical chemistry applied to this one precious rock. The discovery generated massive media attention, but also significant scientific skepticism. Critics point out that mineral precipitation can create circular patterns without biology. Iron and phosphorus concentrations might reflect chemical gradients in the ancient water rather than biological concentration. The organic molecules could be contaminants from Earth or formed through abiotic chemistry. Every feature admits alternative explanation. The researchers acknowledge these possibilities while arguing the totality of evidence points toward biology. This represents exactly the kind of debate science needs. Competing hypotheses tested against observations. More data gradually narrowing the possibilities until consensus emerges. Here's why this matters beyond Mars. If life arose independently on two planets in the same solar system, that suggests life emerges readily wherever conditions permit. The universe might be teeming with biology. Alternatively, if we confirm life on Mars but find it shares common ancestry with Earth life, that tells us organisms can survive interplanetary transfer. Impacts blast rocks from planetary surfaces into space. Some meteorites travel between planets. Life might have originated on one world and spread to others through natural processes. Either scenario has profound implications for how common life might be throughout the galaxy. The search continues beyond surface rocks and meteorites. Scientists now focus on subsurface environments where liquid water might exist today, despite the harsh surface conditions. Temperature increases with depth. On Mars, estimates suggest you'd need to go perhaps 1 or 2 kilometers down before reaching depths warm enough for liquid water, assuming sufficient pressure exists to prevent boiling. Ground-penetrating radar from orbit has detected features interpreted as subsurface water or ice. The European Mars Express orbiter found what appeared to be a lake beneath the South Polar ice cap at about 1.5 kilometers depth. Later analysis questioned that interpretation, suggesting the radar signature might come from clay minerals rather than liquid water. The debate continues. Even if liquid water exists underground, could life survive there? On Earth, life thrives in seemingly impossible places. Deep gold mines in South Africa harbor bacteria living 3 kilometers down, sustained by chemical energy from rock rather than sunlight. Antarctic ice sheets contain liquid water lakes trapped beneath kilometers of ice. Those lakes host active microbial ecosystems. Deep ocean hydrothermal vents support complex communities based on chemosynthesis rather than photosynthesis. Life has colonized every environment on Earth where liquid water exists, no matter how extreme the temperature, pressure, salinity, or radiation levels. If Martian life ever emerged during the planet's wetter past, descendants might persist in similar refuges underground, where conditions remain more favorable than the sterilized surface. The question of subsurface life on Mars hinges partly on methane. This simple molecule, one carbon atom bonded to 4 hydrogen atoms, serves as a potential biosignature. On Earth, methane comes from 2 primary sources: geological processes like volcanic activity and serpentinization, where water chemically reacts with certain minerals, produce some methane. But the overwhelming majority comes from biology. Microorganisms called methanogens generate methane as a metabolic waste product. They consume hydrogen and carbon dioxide, outputting methane. These organisms thrive in oxygen-free environments like swamps, rice paddies, the guts of ruminant animals, and deep subsurface rocks. Finding methane in Mars's atmosphere could indicate similar biological processes occurring underground. NASA's Curiosity rover has been measuring atmospheric methane since landing in Gale Crater in August 2012. The rover carries an instrument called the Tunable Laser Spectrometer, part of the sample analysis at Mars suite. This device can detect methane at concentrations as low as a few parts per billion. Early measurements showed occasional methane spikes. Background levels typically register near or below the detection threshold, but on several occasions concentrations jumped to 7 or 8 parts per billion, then declined back to baseline over subsequent measurements. The pattern suggested localized methane releases occurring near the rover's location, perhaps subsurface pockets of methane occasionally venting through cracks in the rock. Scientists got excited. On Earth, sustained methane production requires either active geology or biology. Mars shows limited geological activity today. No active volcanoes, no plate tectonics. The planet cooled billions of years ago, as its smaller size allowed heat to escape more efficiently than Earth. Without internal heat driving volcanism and crustal recycling, geological methane sources should be minimal. That leaves biology as a strong candidate explanation. Underground microbial communities might be producing methane that occasionally reaches the surface and enters the atmosphere. The rover might literally be parked above a habitable subsurface environment, teeming with methanogenic archaea. But then came the complications. In 2025, a research team published analysis questioning the reliability of Curiosity's methane measurements. The problem involves the instrument's optical chamber. Before analyzing Martian atmosphere, the chamber must be flushed and evacuated. But residual gases might remain, particularly if seals degrade over time. The rover has been operating for over 13 years in harsh Martian conditions. Extreme temperature swings between day and night, pervasive dust, intense ultraviolet radiation all take their toll on equipment. The researchers argued that methane concentrations inside the optical chamber could be 3 or 4 orders of magnitude higher than in the atmosphere being analyzed. If seals leak even slightly, that contamination would produce false positive readings. The reported methane spikes might represent instrument artifacts rather than actual Martian atmospheric methane. Other teams defended the measurements. They pointed out that the spikes show temporal and spatial patterns consistent with environmental release rather than random instrument malfunction. If contamination were the problem, you'd expect more uniform background increases, not sharp spikes followed by rapid declines. Additionally, the European Space Agency's Trace Gas Orbiter, which has been mapping Martian atmospheric composition from orbit since 2016, hasn't detected the methane plumes Curiosity reported. That orbital instrument should be sensitive enough to see concentrations of several parts per billion across regional scales. The absence of detection from orbit doesn't prove the methane doesn't exist. Localized releases might dissipate before spreading widely enough for orbital detection, but it raises questions about how much methane Mars actually produces. Despite these uncertainties, astrobiologists remain interested in methane as a potential biosignature. In 2024, researchers published a detailed study mapping where life could potentially exist on Mars based on methanogen ecology. They started with Earth analogs. Where do methanogens live on our planet? 3 main environments emerged from the analysis. First, microscopic fractures deep within the continental crust. These fractures contain water and support microbial communities that derive energy from chemical reactions between water and iron-bearing minerals. The process produces hydrogen, which methanogens consume. Second, freshwater lakes beneath glaciers. Antarctica hosts several such lakes buried under kilometers of ice. Despite complete darkness and near-freezing temperatures, microbial life persists. Third, hypersaline anoxic basins in the deep ocean. Places like the Mediterranean Sea's brine pools contain water so salty it sinks to the bottom and doesn't mix with the overlying ocean. Despite extreme salinity and zero oxygen, specialized microbes including methanogens thrive there. The researchers then mapped Martian environments that might match these terrestrial analogs. For the crustal fracture environment, they identified regions showing evidence of subsurface water based on radar data and thermal modeling. These areas clustered around the equatorial regions where daytime temperatures occasionally rise above freezing, and at mid-latitudes where ground ice transitions to liquid at depth. For the subglacial lake analog, they pointed to the polar ice caps and certain mid-latitude glacier deposits. Mars has substantial water ice deposits, though whether liquid water exists beneath any of them remains uncertain. For the hypersaline basin analog, they identified ancient lake beds where evaporation would have concentrated salts. If any liquid water remains in these locations today, it would be extremely briny. The study calculated temperature ranges, pH levels, and salinity tolerances for Earth's methanogens. Then they overlaid that data with Martian environmental conditions. The analysis revealed several potential habitable zones. Subsurface regions at depths of 1 to 3 kilometers in equatorial areas might maintain temperatures between 0 and 20 degrees Celsius, perfect for certain methanogen species. Briny groundwater in mid-latitude regions could harbor halophilic methanogens adapted to high salt concentrations. Even beneath polar ice, if geothermal heat creates liquid water pockets, cold-adapted methanogens might survive. The researchers emphasized these represent possibilities, not certainties. Finding suitable conditions doesn't guarantee life actually exists there, but it provides roadmaps for where future missions should explore. Speaking of organic molecules, in March 2025, NASA announced detection of the largest organic compounds ever found on Mars. Curiosity drilled into a rock sample and analyzed the pulverized material using its onboard chemistry lab. The analysis revealed complex carbon-based molecules with chain lengths exceeding 20 carbon atoms. Previous organic detections on Mars involved simpler molecules like methane, formaldehyde, and short-chain hydrocarbons. These longer chains suggest more sophisticated organic chemistry occurred in Mars's past. On Earth, biological processes preferentially create long-chain organics. Lipids, amino acids, nucleotides all involve extended carbon structures. But non-biological processes can also generate complex organics. High temperatures and pressures during meteorite impacts create diverse carbon compounds. Ultraviolet radiation breaking down simpler molecules and recombining the fragments produces complexity through random chemistry. The Martian organics don't prove life existed. They demonstrate that Mars once hosted chemical environments capable of creating the building blocks necessary for life. All these discoveries point toward a compelling conclusion. Life on Mars, if it exists or ever existed, won't be found lounging on the surface. The surface is sterilized by ultraviolet radiation, ionizing radiation from cosmic rays, oxidizing chemistry in the soil, and extreme temperature swings. Anything living there would be destroyed in hours or days. The subsurface offers the only refuge. Vladimir Surdin has spent years thinking about this problem. He gives lectures with deliberately provocative titles like, "We need to explore cosmic underground spaces." The premise is straightforward. On every world except Earth, the surface is inhospitable. Intense radiation, extreme temperatures, vacuum conditions, or crushing atmospheric pressure, toxic chemistry. But underground, conditions moderate. A meter of rock or ice provides excellent radiation shielding. Subsurface temperatures remain more stable than surface temperatures. If water exists, it's underground where pressure prevents evaporation or sublimation. Surdin challenges engineers and programmers to design robots capable of exploring Martian caves. These systems would need to navigate without sunlight, using artificial illumination and sophisticated sensors. They'd need to handle three-dimensional terrain with overhangs, pits, unstable rubble. Communication with surface relay stations might be intermittent as the robot moves deeper underground. Battery life or power generation becomes critical without solar panels. The technical challenges are immense, yet Surdin argues this represents the future of astrobiology. Rovers rolling across the surface taking pictures of rocks have limited value for answering whether life exists on Mars. We need subsurface access, drill rigs capable of penetrating kilometers deep, cave-exploring robots mapping underground networks, sensors detecting gases and liquids seeping from depth. The technology doesn't exist yet in forms suitable for Martian deployment, but it needs to be developed if we're serious about finding life. Consider the Kola super-deep borehole in Russia. Soviet scientists drilled this hole from 1970 through 1992, reaching a depth of 12.262 kilometers. That's deeper than the Mariana Trench is below sea level. The project aimed to study the deep continental crust and test hypotheses about geological structure. What they found surprised everyone. At 7 kilometers depth, they encountered rock saturated with water. Nobody expected liquid water at such depths. The pressure and temperature should have driven all water out, but fractures in the rock contained flowing brine. Microbiological analysis detected bacteria in samples brought up from several kilometers depth. These organisms survive on chemical energy extracted from minerals. They've been isolated from the surface ecosystem for potentially millions of years. If microbes thrive 7 kilometers under Siberia, why not 2 kilometers under Mars? Here's the practical challenge. Drilling 12 kilometers on Earth took decades and cost hundreds of millions of rubles. The drill equipment weighs thousands of tons. Operators adjust procedures in real time based on what the drill encounters. Power comes from reliable electrical grids. Cooling water is abundant. Now imagine doing something similar on Mars. The entire drilling system must be automated because human operators are 100 million kilometers away with communication delays of up to 20 minutes each way. The equipment must fit inside a spacecraft and survive launch, interplanetary cruise, and landing. Power generation relies on solar panels or nuclear batteries with limited output. No water is available for cooling or lubrication. Martian rock might be harder than expected or fractured in ways that cause drill bits to bind. Despite these obstacles, several research teams are developing concepts for Martian drilling. The European Space Agency has studied designs for life detection missions that would drill 2 meters below the surface, then extract and analyze core samples. 2 meters won't reach deep aquifers, but it gets below the zone of maximum surface radiation damage. NASA's Perseverance rover can drill perhaps 10 centimeters into rock. That's sufficient for geological sampling, but barely scratches the surface regarding astrobiology. Future missions will need to drill tens or hundreds of times deeper to reach potentially habitable zones. Some researchers propose hybrid approaches. Send a surface rover to locate cave entrances, then deploy a smaller robot that rappels or climbs into the cave system. This avoids the drilling problem by exploiting natural access points. Mars has thousands of candidate caves identified from orbital imagery. Dark pits where the surface collapsed into subsurface voids. Lava tubes formed by ancient volcanic activity. Networks of interconnected chambers extending for kilometers underground. These caves maintain more stable temperatures than the surface. They block radiation. If water ice sublimates anywhere in the cave system, it might create localized humid environments. Caves represent Mars's most promising habitat for present-day life. Think about what astronauts would do if we sent humans to Mars. NASA talks about building surface habitats, greenhouses, landing pads. But Vladimir Surdin argues the first permanent Mars base will be underground. Not just for radiation protection, though, that's critical. Underground bases maintain thermal stability. Soil and rock provide free structural support. You can pressurize underground chambers without worrying about explosive decompression from meteorite impacts. The construction challenge involves creating livable spaces in Martian regolith or rock, but several techniques look promising. Inflatable structures deployed in lava tubes could create large pressurized volumes. Sintering, using concentrated sunlight or microwave energy to melt and fuse Martian soil into glass-like structures, might create sealed chambers. 3D printing using Martian materials could build walls and ceilings. Once humans establish underground bases, they'll have direct access to potential subsurface water. They'll be positioned to search for extant Martian life in its most likely refuge. Alright, let's shift to Venus now, because that planet presents an entirely different challenge for astrobiology. Where Mars is too cold, Venus is catastrophically hot. Venus represents an extreme opposite to Mars. Where the red planet is too cold and dry, Venus is a hellscape of heat and pressure. Surface temperature averages 460 degrees Celsius, or roughly 860 Fahrenheit. That's hot enough to melt lead, hot enough to make zinc boil. The atmospheric pressure at the surface equals 92 times Earth's sea level pressure. Standing on Venus would feel like being 900 meters underwater on Earth. The atmosphere consists almost entirely of carbon dioxide, with clouds of sulfuric acid floating 40 to 60 kilometers up. Winds at cloud level reach 300 kilometers per hour, creating a super-rotating atmosphere that circles the planet every 4 days, even though Venus itself rotates once every 243 Earth days. The greenhouse effect has gone into overdrive. Solar energy penetrates the atmosphere and heats the surface, but the thick carbon dioxide blanket prevents that heat from radiating back into space. Surface temperatures remain nearly constant day and night, equator to poles. Venus represents what runaway climate change looks like at planetary scale. Scientists want to understand what happened to Venus because it represents Earth's near twin. The two planets have similar size, similar mass, similar bulk composition. Venus orbits slightly closer to the Sun, receiving about twice as much solar energy as Earth. That proximity alone doesn't explain the extreme greenhouse effect. Something went catastrophically wrong in Venus's climate evolution. Early in solar system history, both Earth and Venus likely had oceans. Computer models suggest Venus might have remained habitable for the first 2 billion years after formation. Liquid water covered the surface. The climate was warm but not uninhabitable. Then, a runaway greenhouse initiated. As temperatures rose, ocean evaporation accelerated. Water vapor is itself a greenhouse gas. More evaporation led to more warming, led to faster evaporation in a positive feedback loop. Eventually, all the oceans evaporated. Ultraviolet radiation split water molecules into hydrogen and oxygen. The light hydrogen escaped to space, while oxygen reacted with surface rocks. Venus lost its water permanently. Carbon dioxide accumulated in the atmosphere as volcanic outgassing continued, with no mechanism to recycle it back into rocks. On Earth, plate tectonics and the presence of liquid liquid water allow carbon dioxide to dissolve in oceans, get incorporated into carbonate minerals, and subduct back into the mantle. Venus lacks both plate tectonics and water, so carbon dioxide just keeps building up. The question that keeps climate scientists awake at night is whether Earth could suffer a similar fate. Our planet currently sits comfortably in the habitable zone, where liquid water remains stable. But that zone has boundaries. Push temperatures up too far, and feedback mechanisms might trigger irreversible warming. Consider methane hydrates, also called methane clathrates. These compounds form when methane gets trapped inside ice crystal structures at cold temperatures and high pressures. Enormous deposits exist on Earth's ocean floors and in Arctic permafrost. Estimates suggest several trillion tons of carbon locked up in these deposits. As long as temperatures stay cold and pressures stay high, the hydrates remain stable. But warm the ocean even slightly or melt the permafrost and the hydrates decompose, releasing methane gas. Methane is a far more potent greenhouse gas than carbon dioxide, roughly 30 times more effective at trapping heat over century timescales. Release significant amounts of methane from hydrates and global temperatures spike. That warming destabilizes more hydrates in a feedback loop. Some extinction events in Earth's geological past may have been triggered by massive methane hydrate releases. During one interview, Vladimir Surdin was asked about this threat. He acknowledged the danger but suggested a creative mitigation strategy. Could we engineer bacteria to consume methane before it reaches the atmosphere? Methanotrophs already exist. These microorganisms eat methane as their carbon source, oxidizing it to carbon dioxide and water. They're common in soils, wetlands, and marine environments wherever methane seeps from below. Surdin speculated about deliberately cultivating and releasing methanotrophs in areas where hydrates are decomposing. Convert the methane to carbon dioxide before it enters the atmosphere. Yes, carbon dioxide is still a greenhouse gas, but it's much less potent than methane. You're essentially buying time by swapping a highly dangerous greenhouse gas for a moderately dangerous one. The idea remains theoretical. Nobody has attempted methane mitigation through biological means at scale, but it illustrates the kind of creative thinking required to prevent Earth from following Venus's path. Which brings us to one of the most controversial discoveries in recent planetary science. In September 2020, a team of astronomers led by Jane Greaves from Cardiff University announced detection of phosphine in Venus's atmosphere. They used the James Clerk Maxwell Telescope in Hawaii and the ALMA Observatory in Chile to observe Venus at millimeter wavelengths. Both instruments detected a spectral line consistent with phosphine gas at 20 parts per billion concentration in the cloud layers 50 to 60 kilometers above the surface. On Earth, phosphine is a biomarker. Anaerobic bacteria in oxygen-free environments produce it as a metabolic byproduct. It appears in marshlands, rice paddies, penguin droppings, even human intestines. Outside of biology, phosphine is rare on Earth. Industry can manufacture it, but natural non-biological production is minimal. Finding phosphine on Venus immediately raised the question of whether microbial life might exist in the clouds. The announcement sparked fierce debate. Other research teams attempted to confirm the detection using different instruments and analysis methods. Some succeeded, others failed. In July 2021, researchers using data from the Max Planck Institute's APEX telescope reported they couldn't find phosphine in Venus's clouds. Their upper limit was 7 times lower than the original detection claimed. Either the phosphine doesn't exist, or it's present at much lower concentrations than initially reported, or it varies in time and space such that different observations catch different conditions. The controversy deepened when critics questioned the original data analysis. Spectral line identification is tricky business. Multiple molecules can produce similar signatures at nearby wavelengths. Sulfur dioxide, which is abundant in Venus's atmosphere, creates features that might be confused with phosphine under certain conditions. The debate became technical and heated, with accusations of sloppy analysis on one side and premature skepticism on the other. Then in July 2024, Dave Clements from Imperial College London presented new findings at an astrophysics conference in England. His team had obtained additional observations and reanalyzed both old and new data. Clements announced they'd confirmed the presence of phosphine. The 2020 findings remain robust, he stated. More significantly, they detected ammonia as well. Both phosphine and ammonia are considered potential biomarkers. On Earth, both gases associate with digestive processes in certain organisms. Neither should persist long in Venus's oxidizing atmosphere. Photochemistry and sulfuric acid should destroy them rapidly. Yet they appear to be present, suggesting continuous production from some source. Clements emphasized they weren't claiming definitive proof of life. The chemistry is telling us something unexpected is happening, he said. No known abiotic process can explain the phosphine and ammonia levels we're observing. That doesn't automatically mean biology, but it means we're missing something important about Venus. Venus's atmospheric chemistry. The new data showed higher concentrations in the cloud decks compared to the atmosphere above and below. Phosphine and ammonia both appeared concentrated in a specific altitude range around 50 to 60 kilometers. That's precisely where conditions are most Earth-like on Venus. Temperature hovers near 0 Celsius. Pressure equals roughly 1 atmosphere. You could survive there without a pressure suit, though you'd still need an oxygen supply and protection from sulfuric acid droplets. Multiple researchers have speculated about aerial life on Venus, microorganisms floating in the clouds, harvesting chemical energy, reproducing and dispersing through wind currents. Carl Sagan proposed this idea back in 1967. It seemed like science fiction then. Now, with potential biomarker detections, the concept looks more plausible. Clements assigned a 10 to 20% probability that life exists on Venus. That's his subjective estimate, not a rigorous calculation, but it reflects growing openness to the possibility. Several upcoming missions will investigate further. NASA has approved 2 Venus missions called Da Vinci and Veritas, scheduled to launch in the late 2020s. Europe's Envision orbiter will launch around the same time frame. India's Shukrayan-1 and Russia's Venera-D are in planning stages. China has expressed interest in Venus exploration. Over the next decade, we'll get unprecedented data about Venus's atmosphere, surface, and interior. The phosphine question should be settled definitively. Now let's talk about Mercury, because this planet represents perhaps the most unexpected candidate for harboring life in the solar system. Mercury orbits closest to the Sun, receiving roughly 7 times more solar energy than Earth. Daytime surface temperatures reach 430 degrees Celsius. Nighttime temperatures plunge to minus 180 degrees. The planet lacks a significant atmosphere to moderate these extremes. Conventional wisdom held that Mercury is utterly sterile. Too hot, too cold, too much radiation, no water. But radio astronomers measuring thermal emissions from beneath Mercury's surface discovered something surprising. At the equator, 1 meter below the surface, temperatures stabilize around 67 degrees Celsius. That's warm, but not lethally hot for thermophilic microorganisms. Earth's hot springs and geothermal vents host bacteria thriving at 70 to 80 degrees. Mercury's subsurface at equatorial latitudes offers comparable conditions. Move toward the poles and temperatures drop further. At mid-latitudes, subsurface temperatures average around 20 degrees Celsius, perfect room temperature. Near the poles, permanently shadowed craters maintain temperatures below minus 170 degrees, cold enough to trap water ice. Radar observations from Earth and from the Messenger spacecraft that orbited Mercury from 2011 to 2015 detected highly reflective material in polar craters consistent with water ice. The ice persists because sunlight never reaches these crater floors. Mercury's rotation axis has essentially zero tilt, so polar regions receive only grazing sunlight. Deep craters remain perpetually dark and frozen. Estimates suggest perhaps 100 billion to 1 trillion tons of water ice exists in Mercury's polar regions. Where that water came from remains debated, possibly delivered by comet impacts, possibly outgassed from the interior in Mercury's early history and cold trapped at the poles. Either way, water exists on Mercury. The most intriguing evidence comes from orbital images showing dark deposits inside certain craters. These dark materials absorb sunlight rather than reflecting it, making them appear almost black in photographs. Spectrally, they resemble organic compounds. The leading hypothesis suggests these deposits are carbon-rich materials, possibly including complex organic molecules. On Earth, black deposits in rocks often indicate biological origin. Dead organic matter decomposing into carbon-rich residues. Mercury's dark deposits could be abiotic, formed through chemistry involving carbon brought by meteorites. But their distribution is curious. They appear preferentially in certain craters, suggesting localized processes rather than random meteorite accumulation. Some researchers tentatively suggest these could be biosignatures, evidence of extinct or even extant microbial life dwelling in subsurface habitats and depositing organic waste in specific locations. That's highly speculative. No mission has studied these deposits up close, but the possibility that Mercury, of all planets, might harbor life underground represents how much we still don't know about habitability. Now we head to the outer solar system, where conditions are radically different. Jupiter and Saturn orbit so far from the Sun that surface temperatures plunge to minus 150 degrees Celsius or colder. These gas giants possess no solid surfaces at all. Beneath their visible cloud tops, pressure and temperature increase continuously, until hydrogen transitions from gas to liquid to metallic states. The cores might be rocky, but they're buried under tens of thousands of kilometers of compressed atmosphere. Life, as we understand it, couldn't survive those conditions. The immense radiation belts surrounding these planets add another lethal factor. Jupiter's magnetic field traps charged particles, creating radiation levels that would kill unshielded organisms in hours. Yet despite all this hostility, the outer solar system might harbor more habitable environments than the inner planets. The key lies not on the gas giants themselves, but on their moons. Jupiter has 95 known moons. Saturn has 146. Most are tiny, irregular chunks of rock and ice, probably captured asteroids. But each giant planet has a few large moons comparable in size to Mercury, or even larger. These major moons exhibit remarkable diversity. Io, closest to Jupiter, is the most volcanically active body in the solar system. Tidal forces from Jupiter's gravity squeeze and flex Io continuously, generating enormous internal heat. Hundreds of active volcanoes spew sulfur and silicate lava across the surface. Ganymede, largest moon in the solar system, exceeds Mercury in size, and likely has a subsurface ocean beneath layers of ice and rock. Callisto shows a heavily cratered ancient surface, suggesting geological inactivity for billions of years. And then there's Europa, perhaps the most intriguing moon anywhere. Europa measures 3,100 kilometers in diameter, slightly smaller than Earth's moon. From a distance, it appears brilliant white, reflecting sunlight off a surface composed almost entirely of water ice. Move closer and strange features emerge. Linear cracks crisscross the surface in elaborate patterns. Some cracks extend for hundreds of kilometers. Dark, reddish-brown material fills many of these fractures, possibly salts or sulfur compounds. Large, smooth areas called chaos terrain show jumbled blocks of ice that have broken apart, rotated, and refrozen. The entire surface looks geologically young, perhaps only 20 to 100 million years old based on impact crater counts. For comparison, most planetary surfaces show crater densities indicating ages of billions of years. Europa's surface is constantly being renewed through some active process. Scientists became convinced that a global ocean exists beneath Europa's ice shell based on multiple lines of evidence. First, theoretical modeling of tidal heating. Europa orbits Jupiter in an elliptical path forced by gravitational interactions with the other Galilean moons. As Europa moves closer to and farther from Jupiter, tidal forces squeeze the moon in varying amounts. This flexing generates friction and heat inside Europa, similar to how bending a paperclip back and forth makes it hot. Calculations showed this tidal heating should be sufficient to maintain liquid water under the surface despite Europa's distance from the Sun. Second, magnetic field measurements. Europa has no magnetic field of its own, but when the Galileo spacecraft flew past repeatedly in the late 1990s, it detected an induced magnetic field. Something electrically conductive inside Europa was responding to Jupiter's powerful rotating magnetic field. The best explanation is a global ocean of salty water. Salt dissolved in water creates a conductive fluid. Third, surface features. The chaos terrain, the linear fractures, the lack of high mountains or deep basins all suggest a thin, brittle ice shell floating on a liquid layer. Models indicate the ice shell is probably 15 to 25 kilometers thick. Below that lies an ocean perhaps 100 kilometers deep, making it far deeper than Earth's oceans despite Europa's smaller size. The volume of water in Europa's subsurface ocean likely exceeds all of Earth's oceans combined by a factor of 2 or 3. That's an enormous amount of liquid water. The ocean is salty, based on spectroscopic detection of mineral salts on the surface that probably originated from below. The ocean sits atop a rocky mantle, providing a seafloor where water interacts with rock. This is crucial because on Earth, the interface between water and rock at hydrothermal vents supports rich ecosystems. Chemical reactions between water and certain minerals generate hydrogen, which microbes can use as an energy source. If similar processes occur on Europa's seafloor, the ocean could potentially support life. Understanding whether life might exist in Europa's ocean requires answering several key questions. Does the ocean contain the necessary chemical ingredients? Water is obviously present. Carbon is essential for life as we know it. The James Webb Space Telescope detected carbon dioxide on Europa's surface in September 2023, concentrated in certain geologically young regions. The carbon dioxide likely originated from the subsurface ocean and reached the surface through cracks. That confirms the ocean contains dissolved carbon. Nitrogen and phosphorus, also necessary for biology, likely exist as well based on compositional models of Europa's rocky interior. Energy is the next requirement. Sunlight doesn't penetrate the thick ice shell, so photosynthesis is impossible in the ocean. But on Earth, many ecosystems function without sunlight. Deep ocean hydrothermal vents support communities based on chemosynthesis. Bacteria oxidize hydrogen sulfide, hydrogen gas, or methane, extracting energy to build organic molecules. Those bacteria form the base of food chains that include tube worms, clams, crabs, and fish. Europa's ocean likely has access to similar chemical energy sources. Recent studies have raised concerns about whether Europa's ocean can support life. In March 2024, new measurements from NASA's Juno spacecraft suggested oxygen production on Europa's surface might be far lower than previously estimated. Radiation from Jupiter's magnetosphere bombards Europa's ice continuously. That radiation splits water molecules into hydrogen and oxygen through radiolysis. The hydrogen, being light, escapes to space. The oxygen could potentially sink into the ice and eventually reach the ocean below. Earlier models suggested this process might deliver enough oxygen to support complex metabolism, but Juno's data indicated oxygen production rates are perhaps 10 to 20 times lower than those optimistic estimates. That doesn't necessarily mean the ocean is lifeless. Many Earth microbes don't require oxygen. Anaerobic metabolism works perfectly well for countless species, but it does constrain what types of organisms could potentially exist in Europa's ocean. Another concern emerged from modeling studies presented at the Lunar and Planetary Science Conference in March 2024. Researchers suggested Europa's rocky interior might be geologically inactive. Magma may be unable to penetrate the seafloor to create hydrothermal vents. The rocky mantle might be too rigid to fracture seismically. Without active volcanism or tectonic activity, bringing fresh minerals and heat to the ocean interface, the chemical environment might be too static to drive the kinds of reactions that support life. These findings represent the latest swing in scientific opinion about Europa's habitability. Every few years, new data either increases or decreases our estimate of how likely life is there. The only way to settle the question definitively is to go and look, which brings us to Europa Clipper, NASA's $5 billion mission that launched in October 2024. The spacecraft is currently en route to Jupiter, following a trajectory that includes gravity assists at Mars and Earth to build up velocity. It will arrive in the Jupiter system in April 2030 and begin systematic observations of Europa through a series of close flybys. The mission design is clever. Europa Clipper won't enter orbit around Europa itself because the intense radiation near Jupiter would degrade spacecraft electronics too quickly. Instead, it will orbit Jupiter in an elliptical path that brings it close to Europa, roughly every 2 to 3 weeks. Each flyby passes at different altitudes and over different regions, gradually building up global coverage. Over 4 years, the spacecraft will complete approximately 50 close encounters, some swooping within 25 kilometers of the surface. Europa Clipper carries 9 sophisticated instruments designed to answer specific questions about the Moon's ocean, ice shell, and potential habitability. The Europa imaging system consists of wide-angle and narrow-angle cameras that will map the entire surface at resolutions far exceeding previous missions. These images will reveal geological features in detail, helping scientists understand ice shell dynamics and identify interesting areas for potential future landers. The Europa Thermal Emission Imaging System measures infrared radiation to create temperature maps. Warmer areas might indicate locations where the ice is thinner or where water has recently erupted onto the surface. The Europa Ultraviolet Spectrograph will search for water vapor plumes. The Hubble Space Telescope detected possible plume activity on Europa in 2012, though subsequent observations have been inconsistent. If plumes exist, they provide direct access to subsurface material without needing to drill through the ice. The spacecraft could fly through a plume and sample it directly. The mass spectrometer for planetary exploration will analyze gas and dust particles, determining their composition. If the spacecraft does encounter a plume, this instrument will identify what molecules are present, potentially detecting organic compounds or other biosignatures. The surface dust analyzer complements this by examining dust particles. Together, these instruments characterize the material being ejected from Europa's interior. The mapping imaging spectrometer for Europa operates in the near-infrared, analyzing reflected sunlight to determine surface composition. It will map distributions of water ice, salts, and organics across the surface, revealing where ocean material has reached the exterior. The radar for Europa assessment and sounding will penetrate the ice shell using radio waves. By measuring how those waves reflect and refract, scientists can determine ice thickness and internal structure. They might even detect liquid water pockets within the ice. The Europa Clipper magnetometer will make detailed measurements of Europa's induced magnetic field. By mapping how that field varies, scientists can constrain the depth, salinity, and thickness of the subsurface ocean. The plasma instrument for magnetic sounding extends this work by measuring Jupiter's magnetic field and plasma environment near Europa, providing context for interpreting magnetic measurements. Finally, the mission uses the spacecraft's telecommunications system as a gravity science experiment. By precisely tracking radio signals between Europa Clipper and Earth, scientists can measure tiny variations variations in the spacecraft's velocity caused by Europa's gravitational field. Those variations reveal how mass is distributed inside Europa, distinguishing between scenarios with different ocean depths and ice shell thicknesses. The Europa Clipper mission addresses three fundamental questions. First, does the subsurface ocean exist, and what are its characteristics? While scientists are already confident the ocean is there, precise measurements of its depth, salinity, and chemistry remain needed. Second, what is the ice shell's thickness and structure? Understanding this helps determine how water and nutrients might transfer between the surface and ocean. Third, what is the surface composition and geology? This reveals what materials make up Europa and where ocean material is accessible. Europa Clipper won't definitively answer whether life exists on Europa. The mission isn't designed to detect life directly, but it will determine whether Europa's ocean offers habitable conditions. If the answers are favorable, future missions could target specific locations for drilling or plume sampling, potentially bringing back samples containing definitive evidence. Comparing Europa to Earth highlights both possibilities and challenges. Earth's deepest ocean point, the Challenger Deep in the Mariana Trench, plunges roughly 11 kilometers below sea level. Pressure there reaches 1,000 atmospheres. Temperature hovers just above freezing. Complete darkness prevails since no sunlight penetrates that deep, yet life thrives. When scientists first explored deep hydrothermal vents in the 1970s, they expected barren wasteland. Instead, they found densely populated ecosystems, giant tube worms, clams, mussels, crabs, fish, all living without any connection to the sunlit surface world. Chemosynthetic bacteria form the foundation, converting chemicals dissolved in vent fluids into organic matter. Those bacteria support complex food webs. Some organisms live directly on the bacteria, others graze on bacterial mats. Still others are predators hunting the grazers. Biodiversity at vent sites rivals tropical rainforests. Europa's ocean environment shares some characteristics with Earth's deep sea. Both are dark, cold, and high pressure. Europa's seafloor pressure would be comparable to deep Earth-ocean trenches, perhaps slightly lower due to Europa's weaker gravity. Both environments potentially have rocky seafloors where water interacts with minerals. The differences matter too. Earth's ocean is oxygenated. Photosynthetic organisms at the surface produce oxygen that circulates throughout the ocean depths. That oxygen enables aerobic metabolism, which is far more energy efficient than anaerobic alternatives. Europa's ocean might contain minimal oxygen or none at all. Earth's ocean receives steady input of organic matter from the surface as dead organisms sink. That creates a rain of nutrients. Europa lacks this surface production. Any ecosystem would rely entirely on local chemical energy. Earth's hydrothermal vents supply nutrients continuously as magma rises from the mantle. Europa's geological activity is uncertain. Despite these challenges, the fundamental requirements for life appear to be met on Europa. Liquid water, check. Chemical energy sources, probably. Necessary elements including carbon, nitrogen, phosphorus, probably. Time for life to emerge, yes. Europa's ocean has likely existed for over 4 billion years, as long or longer than Earth's oceans. That gives ample time for chemistry to organize into biology if conditions permit. The question isn't whether life could theoretically exist on Europa. The question is whether it actually does exist there, or whether we'll arrive to find a sterile ocean full of potential but empty of life. Europa faces serious competition in the race to find extraterrestrial life. Saturn's moon Enceladus might actually be the better target. This small world measures just 500 kilometers in diameter, roughly 1/7 Europa's size. You could fit Enceladus inside Texas with room to spare. Despite its diminutive dimensions, Enceladus has captured scientific attention because it does something Europa only hints at. It actively sprays its ocean into space, where we can sample it directly. The discovery happened in 2005, when NASA's Cassini spacecraft approached Saturn for detailed observations. Mission planners originally viewed Enceladus as a low-priority target. The moon looked geologically dead in Voyager images from the early 80s, a small frozen world that had cooled billions of years ago. But Cassini's magnetometer detected something unexpected as the spacecraft flew past. Saturn's powerful magnetic field was being perturbed near Enceladus. Something was pushing against those magnetic field lines, an atmosphere perhaps, or gas venting from the surface. Scientists immediately requested a closer look during the next orbital pass. When Cassini turned its cameras toward Enceladus's south pole, the images revealed something nobody anticipated. Enormous jets of material shooting hundreds of kilometers into space. Water vapor mixed with ice particles fountaining from 4 parallel fractures nicknamed tiger stripes. Scientists calculated the eruption rate at roughly 250 kilograms per second. That's about 550 pounds every second continuously. The jets accelerate to speeds exceeding 2,000 kilometers per hour, before dispersing into space. Some material falls back to the surface as snow, gradually accumulating over geological time. The rest escapes Enceladus's weak gravity entirely. That escaped material forms Saturn's E-ring, a tenuous disk of ice particles extending from well inside Enceladus's orbit to beyond the orbit of the larger moon Rhea. Astronomers had known about the E-ring for decades. Cassini revealed its source. Scientists immediately recognized what this meant. Enceladus has a subsurface ocean connected to the surface through fractures in the ice. The geysers provide direct access to that ocean. Cassini flew through the plume during subsequent passes, collecting and analyzing samples with its onboard instruments. The cosmic dust analyzer measured particle sizes and compositions. The ion and neutral mass spectrometer identified gas molecules. Together, these instruments characterized what was erupting from beneath Enceladus's surface. Water vapor dominated, as expected, but the plume also contained carbon dioxide, methane, ammonia, molecular hydrogen, and complex organic compounds. Salinity measurements indicated dissolved sodium chloride, table salt. The ocean is salty like Earth's oceans. The organic compounds particularly excited astrobiologists. Simple molecules like methane and formaldehyde appeared alongside more complex species. Scientists detected propane, acetylene, formaldehyde, and traces of benzene. In 2018, researchers announced detection of heavy organic molecules with masses exceeding 200 atomic mass units. These large, complex organics suggested sophisticated chemistry occurring in Enceladus's ocean. The densest concentrations of organic material clustered near the warmest tiger stripe fractures, hinting that active chemistry might be producing these compounds continuously rather than representing ancient material being passively vented. The most tantalizing discovery came from silica nanograins detected in the E-ring. These tiny particles, measuring just 6 to 9 nanometers across, can only form under specific conditions. Liquid water must interact with rock at temperatures exceeding 90 degrees Celsius. The chemical reactions that produce these nanograins require both heat and time. The most plausible explanation involves hydrothermal vents on Enceladus's seafloor. Hot water emerging from cracks in the rocky core dissolves silica. As that superheated fluid mixes with the colder ocean water, dissolved silica precipitates out as nanograins. The particles get swept up in currents, eventually reaching the geysers and erupting into space. Finding these nanograins proved that Enceladus has active geology at the ocean-rock interface, exactly the kind of environment that supports life on Earth. Then, on October 13, 2025, just days ago, researchers published a groundbreaking study in Nature Astronomy, announcing detection of previously unknown organic compounds in Enceladus's plume. The team reanalyzed archival data from Cassini's final flybys in 2015 using improved computational techniques and better understanding of instrument calibration. They identified nitrogen-bearing compounds including hydrogen cyanide and cyanoacetylene. Both molecules serve as building blocks for amino acids and nucleotides. On Earth, hydrogen cyanide participates in prebiotic chemistry pathways that could lead to life's emergence. Finding it actively being produced on Enceladus strengthens the case for potential habitability. The researchers also detected oxygen-bearing organics and sulfur compounds at higher concentrations than previously recognized. The diversity and complexity of Enceladus's organic chemistry rivals what we observe in comets, but with the crucial difference that Enceladus's compounds come from a liquid water environment potentially suitable for biology. Comparing Enceladus to Europa reveals both similarities and crucial differences. Both moons hide global oceans beneath ice shells. Both experience tidal heating from their respective giant planets. Both show evidence of active geology connecting their oceans to their surfaces. But Enceladus has advantages for astrobiology missions. The geysers eliminate the need for drilling or melting through the ice. A spacecraft can fly through the plume, collect samples, and analyze them without ever landing. Europa's possible plumes remain inconsistent. Hubble detected potential water vapor emissions in 2012 and 2014, but subsequent observations haven't confirmed regular activity. Europa Clipper will search systematically for plumes during its flybys, but they might not exist at all, or might occur sporadically in ways difficult to catch. Enceladus erupts continuously, making sampling straightforward. Europe's space agency is planning a mission called the Enceladus Orbilander, currently in concept development. The mission design includes 2 phases. First, an orbiter would spend several years characterizing Enceladus globally, mapping surface features, measuring ice thickness, confirming ocean properties. The orbiter would repeatedly fly through the geysers, collecting fresh samples and analyzing them with sophisticated instruments far more capable than what Cassini carried. Then in the mission's second phase, a lander would deploy to the surface near the South Polar region. The lander would collect ice samples deposited by geyser fallout. That ice contains frozen droplets of ocean water along with organic compounds and minerals. Laboratory quality analysis could determine whether amino acids, lipids, or other biomolecules are present. The mission could even search for cellular structures or other direct evidence of life. Launch might occur in the early 2030s with arrival at Saturn roughly a decade later. The mission represents humanity's best near-term opportunity to definitively answer whether life exists beyond Earth. Saturn has other moons worth mentioning. Titan, larger than Mercury, remains the only moon in the solar system with a thick atmosphere. Nitrogen dominates at 1.5 atmospheres surface pressure. Methane and ethane rain from the sky, forming rivers, lakes, and seas. The Cassini-Huygens mission revealed a remarkably Earth-like landscape despite temperatures of -180 degrees Celsius, where methane plays the role water plays on Earth. Titan almost certainly has a subsurface water ocean like Europa and Enceladus, but the surface hydrocarbon lakes might support exotic non-water-based life chemistries. NASA's Dragonfly mission, scheduled to launch in 2028, will send a nuclear-powered quadcopter to explore Titan's surface. The drone will fly between dozens of sites, analyzing surface chemistry and searching for biosignatures. Jupiter's moon Ganymede, the solar system's largest moon, probably has a subsurface ocean as well. Its icy surface shows evidence of past tectonic activity. Callisto, Jupiter's second-largest moon, might host an ocean deep beneath a heavily cratered ancient surface. The outer solar system contains multiple ocean worlds. We've barely begun exploring them. Now let's shift our focus outward to planets orbiting other stars. The exoplanet revolution began in the mid-90s when astronomers developed techniques sensitive enough to detect Jupiter-sized worlds orbiting nearby stars. The discoveries came slowly at first. One planet in 95, a handful more by the end of the decade. Then detection methods improved. The Kepler Space Telescope launched in 2009 and began finding planets by the hundreds. Today we've confirmed 7,900 exoplanets with thousands more candidates awaiting verification. These worlds exhibit stunning diversity. Hot Jupiters orbit closer to their stars than Mercury orbits our Sun, with surface temperatures exceeding 2,000 degrees. Super-Earths with masses between Earth and Neptune occupy a size range we don't see in our solar system. Mini-Neptunes shrouded in thick hydrogen atmospheres. Rocky worlds similar to Mars or Venus. Water worlds potentially covered entirely by global oceans hundreds of kilometers deep. The variety challenges our theories of planet formation and evolution. Most early detections found massive planets because large worlds create bigger signals. Jupiter-mass planets cause their stars to wobble noticeably as gravitational attraction pulls the star and planet around their common center of mass. Giant planets also block significant starlight when they transit across their star's disk as seen from Earth. Smaller planets produce subtler effects requiring more sensitive instruments and longer observation baselines. By the 2010s, detection capabilities had advanced enough to find Earth-sized worlds. The Kepler mission discovered over 2,500 confirmed planets before the spacecraft failed in 2018. Its successor, TESS, the Transiting Exoplanet Survey satellite, continues the search. Ground-based surveys using radial velocity and direct imaging methods add to the catalogue. As of today, we know of several dozen planets with sizes between half and twice Earth's diameter orbiting in their stars' habitable zones, where surface temperatures could support liquid water. But finding Earth-sized planets in habitable zones represents just the first step. Determining whether those worlds actually have water, atmospheres, and conditions suitable for life requires spectroscopy. Analyzing starlight filtered through exoplanet atmospheres during transits reveals what gases are present. Water vapor, carbon dioxide, methane, oxygen, all leave characteristic signatures. The James Webb Space Telescope has revolutionized exoplanet atmospheric characterization since beginning operations in 2022. Its infrared sensitivity can detect molecules in planet atmospheres light years away. Several potentially habitable worlds have moved to the top of the observation queue. One planet in particular has generated enormous excitement. K2-18b orbits an M-dwarf star 120 light-years from Earth in the constellation Leo. Discovered in 2015 by Kepler, the planet has a mass about 8 to 9 times Earth's and a radius roughly 2.6 times larger. That size and mass suggest a composition intermediate between rocky planets like Earth and gas dwarfs like Neptune. Models indicate K2-18b likely has a rocky core surrounded by a thick water envelope topped by a hydrogen-rich atmosphere. The planet orbits its star every 33 days at a distance where temperatures could support liquid water on the surface or in the atmosphere. M-dwarf stars are smaller and cooler than our Sun, so their habitable zones lie much closer in. K2-18b receives roughly the same amount of stellar energy Earth receives from the Sun, maybe slightly less. In September 2023, a team led by Niku Madhusudan from Cambridge University announced detection of dimethyl sulfide in K2-18b's atmosphere using James Webb data. This molecule, often abbreviated DMS, is produced on Earth almost exclusively by biological processes. Marine phytoplankton generate it when breaking down dimethyl sulfonopropionate, a compound that helps regulate cellular salt concentrations. When you smell the ocean from a beach, you're smelling DMS. Finding it on K2-18b raises the tantalizing possibility that life might exist there. The detection remains preliminary, requiring confirmation from additional observations. But if verified, it would represent the first potential biosignature detected on an exoplanet. The most direct evidence yet that we might not be alone in the universe. The detection of dimethyl sulfide on K2-18b represents a watershed moment in astrobiology, but the scientific community remains appropriately cautious. A single detection, no matter how intriguing, requires independent verification before acceptance. The problem is that only one instrument currently has the sensitivity to analyze K2-18b's atmosphere in sufficient detail. The James Webb Space Telescope operates at infrared wavelengths where water vapor, carbon dioxide, methane, and dimethyl sulfide all produce distinctive absorption features. Webb's 6.5-meter primary mirror collects enough light from distant stars to detect subtle changes when planets pass in front. But Webb is booked solid with observation requests from astronomers worldwide. Getting additional time to re-observe K2-18b competes against thousands of other compelling targets. The team that made the initial detection will certainly get follow-up observations. Probably within the next year or two, they'll look for the dimethyl sulfide signature again to confirm it wasn't an artifact of data processing or instrument calibration. But confirmation from a completely independent instrument would carry far more weight. Webb won't last forever. The spacecraft carries limited fuel for maintaining its position at the L2 Lagrange point 1.5 million kilometers from Earth. Mission planners estimate operational lifetime through 2033, possibly extending to 2035 if they manage fuel carefully. Eventually, Webb will run out of propellant and drift, ending its mission. Before that happens, another space telescope needs to come online with comparable or superior capabilities. NASA has approved the Habitable Worlds Observatory as a flagship mission for the 2040s, but that launch date is far in the future. The European Space Agency is developing the Ariel mission, scheduled to launch in 2029. Ariel will specialize in exoplanet atmospheric characterization, observing hundreds of worlds to build statistical understanding of atmospheric chemistry. It could provide independent confirmation of K2-18b's dimethyl sulfide, if the molecule is really there. Ground-based telescopes also have a role to play. The extremely large telescope, currently under construction in Chile's Atacama Desert, will have a primary mirror 39 meters across. That's larger than a basketball court. It will be the largest optical telescope ever built. The massive light-collecting area combined with adaptive optics systems that correct for atmospheric distortion will enable spectroscopy of exoplanet atmospheres from the ground. First light is scheduled for 2027. Once operational, the ELT could observe K2-18b during transits and search for dimethyl sulfide. But atmospheric water vapor interferes with some infrared observations from the ground, even at high-altitude dry sites. The ELT might not have sufficient sensitivity in the exact wavelength range where dimethyl sulfide absorbs most strongly. Still, it represents an independent check that could either confirm or refute the Webb detection. Assuming the dimethyl sulfide detection holds up under scrutiny, what would it actually mean? On Earth, phytoplankton in the ocean produce dimethyl sulfide when breaking down DMSP, a molecule that helps cells regulate osmotic pressure. The phytoplankton release DMS into seawater, where it diffuses into the atmosphere. Wind carries it inland, giving coastal areas that characteristic ocean smell. DMS also seeds cloud formation by providing particles for water vapor to condense around, creating a feedback mechanism that might help regulate Earth's climate. Finding DMS on K2-18b would suggest similar biological processes occurring there. But we need to be careful about assuming Earth-like biochemistry. K2-18b orbits an M-dwarf star, not a Sun-like G-type star. M-dwarfs emit most of their energy in the infrared rather than visible light. Any photosynthesis on such a world would need to adapt to that different spectrum. The planet likely has one hemisphere permanently facing its star due to tidal locking, creating extreme day-night temperature gradients. The atmosphere and ocean would need to circulate heat efficiently to maintain habitable conditions. The planet's mass, 8 times Earth's, means surface gravity would be significantly higher, affecting how atmospheres stratify and how organisms could move. Life on K2-18b, if it exists, would face very different selective pressures than life on Earth. The distance to K2-18b, 120 light-years, makes any direct exploration impossible with current or near-future technology. Even traveling at 1% the speed of light would require 12,000 years to reach it, but there are much closer targets. Proxima Centauri, the nearest star to our solar system, sits just 4.24 light-years away. This red dwarf star has at least 2 confirmed planets. Proxima Centauri b discovered in 2016, orbits in the star's habitable zone. The planet's mass is at least 1.17 times Earth's mass, making it potentially rocky. It completes one orbit every 11.2 days. That sounds incredibly fast compared to Earth's 365-day year, but Proxima Centauri is much smaller and dimmer than our Sun. The habitable zone lies much closer to the star. Proxima b receives slightly more stellar energy than Earth receives from the Sun, perhaps 30% more. Whether that's compatible with surface habitability depends on atmospheric composition and planetary albedo. The challenges of studying Proxima b are significant. The planet doesn't transit its star as seen from Earth, so we can't use transit spectroscopy to analyze its atmosphere. Direct imaging is extremely difficult because the planet's faint reflected light is overwhelmed by the star's glare. Proxima Centauri is also a flare star, producing sudden intense bursts of X-rays and ultraviolet radiation that could strip away planetary atmospheres over time. Whether Proxima b retains a thick atmosphere and magnetic field for protection remains unknown, but the proximity makes it the most obvious target for humanity's first interstellar probe. 4 light-years is still an enormous distance. The fastest spacecraft we've ever built, the Parker Solar Probe, reaches about 430,000 miles per hour at perihelion. At that speed, reaching Proxima Centauri would take roughly 6,700 years. The Voyager spacecraft, launched in 1977 and now in interstellar space, travel at about 38,000 miles per hour. They would need over 70,000 years to cover 4 light-years. Clearly, we need radically faster propulsion to make interstellar exploration feasible within human timescales. Chemical rockets are useless. They depend on carrying propellant and expelling it at high velocity to generate thrust. The amount of propellant needed to reach a significant fraction of light speed exceeds what any rocket could carry. Nuclear propulsion offers some improvement. Fission or fusion reactions release millions of times more energy per kilogram than chemical reactions. Project Orion, studied in the 1950s and 60s, proposed detonating nuclear bombs behind a spacecraft and riding the shockwave. Theoretical calculations suggested this could achieve a few % of light speed, but the technical challenges are immense, and the political obstacles to launching nuclear weapons into space are probably insurmountable. Ion drives and plasma engines provide continuous low thrust over years, eventually building up high velocities. NASA's Dawn mission used ion propulsion to explore the asteroid belt, but even optimized ion drives struggle to achieve velocities sufficient for interstellar travel within reasonable timeframes. Which brings us to Yuri Milner and the Breakthrough Starshot project. Milner is a Russian-Israeli entrepreneur and physicist who made billions in internet investments. He studied physics at Moscow State University before moving into business, but he never lost his fascination with space exploration and the search for extraterrestrial intelligence. In 2016, Milner announced Breakthrough Starshot, an initiative to develop technology for sending small robotic probes to Alpha Centauri at 20% the speed of light. The concept relies on light sails, sometimes called solar sails or photon sails. The principle is straightforward. Light carries momentum. When photons hit a reflective surface, they transfer momentum just like balls bouncing off a wall. The momentum transfer per photon is tiny, but with enough photons hitting a large enough sail, you can generate meaningful acceleration. Solar sailing has been demonstrated on multiple missions. Japan's Icaros probe used solar pressure for attitude control and propulsion. NASA's NanoSail D deployed a small sail in Earth orbit. The Planetary Society's light sail missions successfully tested sail deployment and attitude control, but using sunlight alone provides relatively weak acceleration. The sun's intensity drops off as 1 over distance squared. By the time you reach the outer solar system, solar pressure is negligible. Breakthrough Starshot proposes solving this problem with a ground-based laser array. Imagine a field of lasers in a high-altitude desert location, perhaps Chile or Hawaii. These lasers, possibly numbering in the thousands, would aim at a departing spacecraft and fire in unison. The combined laser beam would deliver gigawatts of power to a light sail measuring about 4 meters by 4 meters. The sail material would need to be incredibly thin and reflective, perhaps just a few hundred atoms thick, made from advanced materials like graphene or aluminum-coated polymers. The probe itself would be miniaturized to perhaps 1 gram of mass, a tiny chip containing cameras, communication equipment, sensors, and minimal electronics. This nanocraft would accelerate under constant laser illumination for minutes or hours, eventually reaching 20% of light speed. At that velocity, the journey to Proxima Centauri would take roughly 20 years. The probe would coast most of the way in silence, its systems powered down to conserve energy. As it approached the target system, it would wake up, activate cameras and sensors, and gather data during the flyby. The encounter would be brief, lasting hours at most. Then the probe would transmit data back to Earth using a tiny laser, beaming information across 4 light-years of space. That transmission would take another 4 years to arrive. So from launch to data reception, the mission requires roughly 24 years, long by human standards but achievable within a single generation. Multiple probes could launch in succession, improving redundancy and providing multiple observation opportunities. The technical challenges are staggering. The laser array requires extraordinary precision. If the beam wavers even slightly, it will miss the sail entirely. Atmospheric turbulence distorts laser beams, so adaptive optics would be essential. The sail must be perfectly reflective, or it will absorb laser energy and vaporize. The spacecraft must survive acceleration forces of perhaps 50,000 Gs. That rules out any mechanical components that could break. Interstellar space contains dust particles, and hitting even a grain of sand at 20% light speed would destroy the probe. The communication system must transmit data from enormous distance with minimal power. The electronics must survive decades of cosmic ray exposure without shielding, and the entire system must be economically viable, costing perhaps hundreds of millions rather than tens of billions. Otherwise, no funding agency will support it. Boris Chertok, a legendary Soviet rocket engineer who worked alongside Sergei Korolev, expressed deep skepticism about breakthrough starshot during interviews before his death. Chertok argued the technical obstacles are insurmountable with current or near-future technology. The energy requirements alone seem prohibitive. Accelerating even a 1-gram payload to 20% light speed requires roughly 30 million joules of kinetic energy. Achieving that with laser propulsion efficiency of perhaps 30% means delivering 10 times more energy from the lasers. For comparison, that's equivalent to detonating several kilograms of TNT, all focused on a sail the size of a small room, in mere minutes. The thermal management challenges are nightmarish. Any absorption of laser energy would instantly vaporize the sail. Vladimir Surdin, while more optimistic than Chertok, acknowledges these difficulties. But Surdin views them as engineering problems rather than fundamental physics barriers. Engineering problems can be solved with sufficient funding and clever design. Physics barriers are insurmountable. The debate reflects different philosophies about technological progress. Skeptics point to numerous failed predictions about imminent breakthroughs. We were supposed to have flying cars, fusion power, and moon bases by now. Extrapolating current technology into utopian futures has a poor track record. Optimists counter with examples where the seemingly impossible became routine. Heavier-than-air flight seemed impossible to many scientists before the Wright brothers succeeded. Breaking the sound barrier was thought to pose insurmountable physical barriers. Reaching the moon was science fiction until Apollo. Nuclear energy, computers, the internet, all faced expert skepticism before proving viable. The difference between impossible and merely difficult often becomes clear only in hindsight. Whether we develop light sail technology or some other propulsion method, the fundamental question remains: how would we detect signs of intelligence on distant worlds? Traditional SETI programs have searched for radio signals for over 60 years with 0 confirmed detections. The reasoning is sound. Radio waves travel at light speed and penetrate interstellar gas clouds. Any technological civilization would likely discover radio communication early in their development, just as we did in the late 19th century. But radio has limitations. Broadcast power drops as 1 over distance squared. Even our most powerful transmitters become undetectable beyond a few hundred light-years unless you have an absurdly large receiving antenna. Targeted laser communication might be far more efficient. Consider the Baikal Neutrino Telescope in Siberia. This facility consists of strings of photodetectors suspended in Lake Baikal, the world's deepest freshwater lake. The detectors sit more than a kilometer below the surface, shielded from cosmic ray interference by the water above. The primary mission involves detecting neutrinos from cosmic sources. When a neutrino interacts with water molecules, it produces a charged particle that travels faster than light speed in water, creating Cherenkov radiation. The photodetectors catch these faint flashes of blue light. Vladimir Surdin points out that this same technology could detect optical pulses from distant civilizations. If an advanced society wanted to communicate across interstellar distances, they might use powerful lasers. A sufficiently intense laser pulse arriving at Earth would produce detectable Cherenkov radiation in large bodies of water or ice. The signal would be brief, perhaps nanoseconds long, but unmistakable in its artificial pattern. Optical SETI programs have begun searching for such signals. Several observatories now conduct surveys looking for brief laser flashes from nearby stars. The advantage over radio is bandwidth. Optical frequencies can carry far more information per second than radio. The disadvantage is precision. You need to aim your laser beam extremely accurately. Miss your target star system by a tiny fraction of a degree, and your signal vanishes into the void. But an advanced civilization that has mapped their galactic neighborhood could target specific star systems likely to harbor technological species. They might send pulses to thousands of candidate systems, repeating the transmission periodically in case anyone happens to be looking at the right moment. We're beginning to conduct similar searches. Facilities like the panoramic SETI experiment at the Keck Observatory scan the sky for optical transients that might represent artificial beacons. So far, the results are null, no confirmed laser signals, but the search has barely begun. Which brings us to the Fermi paradox, named after physicist Enrico Fermi, who supposedly asked, "Where is everybody?" over lunch at Los Alamos in 1950. The paradox arises from the apparent contradiction between high probability that intelligent life should be common in the universe and the complete absence of evidence for such life. Consider the numbers. We've now confirmed 7,900 exoplanets. Most stars have planets. Estimates suggest the Milky Way galaxy contains 200 to 400 billion stars. Even if only a small fraction have Earth-like worlds in habitable zones, that still yields billions of potentially habitable planets in our galaxy alone. The galaxy is 13 billion years old. Earth is 4.5 billion years old. Many star systems are billions of years older than ours. If intelligent life arose on any of those worlds and developed technology, they've had enormous time to expand throughout the galaxy. Yet we see no evidence, no megastructures, no artificial transmission, no sign anyone has ever visited Earth. The silence is deafening. Dozens of explanations have been proposed. Maybe intelligent life is extremely rare. Maybe technological civilizations destroy themselves shortly after reaching our level of development. Maybe they exist but stay quiet to avoid detection by hostile species. Maybe they've transcended physical existence and no longer build things we can detect. Maybe the distances between stars are too vast for practical travel or communication, despite millions of years of development. Maybe we're looking in the wrong ways or at the wrong times. Maybe they're here, but we're too primitive to recognize them. The range of possibilities extends from depressing to terrifying to wildly speculative. None can be ruled out conclusively. Recent studies have raised another possibility worth considering. Perhaps life itself is common, but intelligence is rare. Earth hosted life for roughly 3 billion years before multicellular organisms evolved. Another 500 million years passed before anything resembling intelligence appeared. Human-level intelligence emerged only in the last few million years, and technological civilization began just a few thousand years ago. That's a tiny fraction of Earth's history. Intelligence might not be an inevitable outcome of evolution. It requires specific selection pressures, environmental conditions, and contingent historical events that might rarely align. Microbial life could be ubiquitous, while intelligence remains vanishingly rare. If that's correct, we might detect biosignatures on many exoplanets, but never find anyone to talk to. The implications cut to fundamental questions about humanity's purpose and future. Vladimir Surdin argues that preserving life represents the highest goal our species can pursue. Life arose on Earth 4 billion years ago through processes we don't fully understand. It survived multiple mass extinctions, adapted to changing conditions, and eventually produced beings capable of contemplating their own existence. That achievement is precious beyond measure. But life on Earth faces existential threats. Climate change, nuclear weapons, asteroid impacts, supervolcanic eruptions, any could devastate global ecosystems. On geological timescales, Earth itself will become uninhabitable. The sun is gradually brightening as it ages. In roughly 1 billion years, Earth's oceans will boil away. In 5 billion years, the sun will expand into a red giant, engulfing the inner planets. Life's tenure on Earth is temporary. If we want the story to continue, we must eventually spread beyond our homeworld. Mars represents the obvious first step. Over the past decade, serious planning has begun for permanent human presence on the red planet. Surdin suggests the first Mars base could be operational within 10 years, if funding and political will align. The technical capabilities exist. SpaceX is developing the Starship system specifically for Mars missions. The spacecraft could carry 100 tons of cargo or 100 passengers to Mars per flight. Multiple flights over several years could deliver everything needed for a self-sustaining settlement. Water ice exists in abundance. The soil contains minerals that can be processed into building materials. Carbon dioxide atmosphere can be split into oxygen and carbon monoxide. Solar panels generate power. The main challenges are social and economic rather than purely technical. Can humans maintain psychological health during multi-year missions? How do you create viable governance structures for Martian colonies? What economic model justifies the enormous investment required? These questions lack clear answers. A permanent Mars colony, fully independent of Earth supply runs, remains decades away at minimum. The technology for in-situ resource utilization needs development. Life support systems must achieve near-perfect recycling efficiency. Medical capabilities must handle trauma and disease without access to Earth's hospitals. The population needs genetic diversity to remain viable long-term. You probably need at least several hundred people, possibly thousands, to maintain a stable breeding population and preserve technological knowledge. Getting that many people to Mars and keeping them alive requires infrastructure we haven't built yet. But the longer-term vision extends beyond Mars. Asteroid mining could provide resources for space-based manufacturing. Orbital habitats might eventually house millions. Settlements on Europa or Enceladus could tap subsurface oceans. Interstellar missions might seed life throughout the galaxy. These ambitions sound like science fiction, but so did everything we've accomplished in space during the past 70 years. Now let's return to where we began, 3I/Atlas, the interstellar visitor that sparked 2 hours of discussion about alien spacecraft, ancient Martian oceans, phosphine on Venus, subsurface seas on icy moons, and biosignatures on distant exoplanets. As we approach the end of October 2025, the comet has passed perihelion and begun its outbound journey. By early November, it will have moved beyond Venus's orbit. Throughout December, it will cross the zone between Earth and Mars, gradually fading as distance from the Sun increases. Observatories worldwide will continue tracking it, gathering data until it becomes too faint to detect. Probably by February or March 2026, 3I/Atlas will fade below the detection threshold of even the largest telescopes. It will continue outward in silence, headed back into interstellar space. Centuries from now, it will cross the Kuiper Belt. Millennia from now, it will leave the Oort cloud. Eventually, it will travel among the stars once more, perhaps encountering other planetary systems on its endless journey through the galaxy. Scientists will analyze the accumulated data for years. Papers will be published debating every aspect of the object's composition, trajectory, and origin. Avi Loeb's hypothesis of artificial origin will remain controversial. Most astronomers will conclude 3I/Atlas was a natural comet with unusual but explicable characteristics. A minority will argue the questions remain open. The debate will fade as attention shifts to other topics, other discoveries, other mysteries, unless something dramatic happens. If 3I/Atlas deviates from its predicted trajectory during the outbound phase, if it performs a gravitational maneuver using Jupiter or Saturn that can't be explained by natural forces, if it emits an artificial signal, any of these would reignite the controversy spectacularly. For now, we watch and wait. One certainty emerges from this experience. We're no longer unprepared for interstellar visitors. Plans are underway to maintain a spacecraft on standby, ready to intercept the next object that enters our solar system from beyond. When the fourth interstellar visitor arrives, and eventually one will be positioned to study it far more thoroughly than we studied Oumuamua or even 3I/Atlas. That spacecraft will carry instruments capable of detailed analysis. It might approach close enough to image surface features directly. Depending on the object's trajectory and velocity, we might even achieve rendezvous, matching speed and orbiting alongside for extended observation. The data gathered could finally settle questions about whether interstellar objects show signs of artificial construction or remain purely natural phenomena. So are we alone in the universe? After 2 hours of examining evidence, the honest answer is, we don't know. We have tantalizing hints: organic compounds in Martian rocks, phosphine in Venusian clouds, subsurface oceans on Europa and Enceladus teeming with chemical energy, dimethyl sulfide detected on K2-18b, 7,900 exoplanets including dozens that might resemble Earth. The building blocks of life appear common throughout the cosmos. The basic requirements for biology seem satisfied on multiple worlds. Yet we haven't found definitive proof. Every potential biosignature admits alternative explanations. Every anomaly might be natural rather than artificial. The search continues because the question matters profoundly. Discovering life beyond Earth, even microbial life, would revolutionize our understanding of biology's universality. Finding intelligent life would transform everything about how we view our place in the cosmos. The universe has shown us wonders beyond imagination. Galaxies billions of light years distant, black holes warping space-time, neutron stars spinning hundreds of times per second, planets where it rains glass sideways, moons with subsurface oceans, stars being born and dying, and Earth, an ordinary rocky world, orbiting an unremarkable star in an average galaxy, somehow produced life that evolved into beings capable of contemplating all this. We've gone from thinking Earth was the center of everything to understanding we're one planet among billions, in one galaxy among trillions. The journey of discovery continues. Every answer raises new questions. Every observation reveals new mysteries. Here's my question for you. After everything we've discussed, what do you think? Is 3I/Atlas a natural comet that happened to have unusual characteristics? Or is there something to Avi Loeb's argument that we're seeing signs of artificial construction? Leave your answer in the comments. I want to hear your reasoning. What would it take to convince you one way or the other? And here's something worth considering. 90% of people have no idea these discoveries are happening. They don't know about the rock NASA found on Mars that might contain fossilized bacteria. They've never heard of dimethyl sulfide on K2-18b. They don't realize Europa Clipper is on its way to explore an ocean that might harbor life. Share this video. Get the conversation started, because these are the most important questions humanity can ask. Are we alone? What is our place in the cosmos? What is our responsibility to life itself? The answers might be closer than we think,